Cool. Okay, hello everyone. Thank you very much for coming to today's AIAA Los Angeles Las Vegas section town hall meeting on Saturday, March 20th. Today we have a great guest speaker on a very exciting topic, and we'll know more about his research activity, and this is very inspiring. Okay, so this is general schedule. We kind of a few minutes late, but we'll catch up. It's a little bit flexible, so we'll catch up the schedule, don't worry. So just a few words, and we actually have been trying to work on some events related to gravity, warp drive. We have few talks, and we try to get a legal person, the gravity interferometry people from Caltech, but kind of postponed. So we actually have been very interested in this topic, the quantum gravity, universe, astrophysics. Basically, with this event we're doing is to inspire people. It's not intended to sell certain kind of product or theory, but it's kind of people understand what's going on, state of the art, and get inspired and networking each other. So before the event, we have some logistic. First, we thank the AIAA headquarters, the national office, who provide the platform, the Zoom, which is actually very expensive. So really highly appreciated. So this session will be recorded, so it will be posted online. And thanks to our speaker, Mr. Stuart Maronway, who will permit us to do so. So during the process, if you somehow because internet you got disconnected, please keep trying to reconnect. It could be just temporary. The audio, if you have bandwidth is limited, you can try to call in and just use the internet for viewing the slides of camera, video, but you can dial in to reduce the bandwidth load on the internet. One thing is, generally this event are for networking, but to protect the privacy, people won't know you are in the meeting for the attendees. If you want to let people know you are here and want to chat with people, please utilize the chat box. And there's a Q&A box, which the speaker can view the question. So you're welcome to type your question in the Q&A box. And more toward the end of the talk, if you raise your hand, we can unmute you and you can speak out directly to the speaker and ask questions. So if you're concerned about the security and privacy, Zoom has improved a lot. But please don't talk about any national security or personal information. And if you're concerned about the Zoom app, you can try to dial in. Okay, so just try to, and just a few words about Southern California. We are blessed to be in this area because heavily aerospace populated. And we are just chatting with the speaker, Mr. Maronway. That's the Space Web Telescope is a great example of what he's going to talk about today's astrophysics. And it's great work by the engineers. It's a very big project. It's going to be launched pretty soon. And we also here we have a defense contractor making the fighter jet, and also the new trend, sustainable aviation, electric hybrid, hydrogen, biofuel, and we just have the Mars 2020 Perseverance landing, on Mars, very exciting. And we have a lot of experts, space debris, asteroid defense, mining, space tourism. Of course, we have SpaceX, very exciting, and a lot of students doing great projects. So just a few words about Black History Month, because last week, and this is with a permission from our speaker today, because to this event as the Black History Month event, it's actually February because we planned this event in February, but we just have to find the schedule in March. And in January, we have a great ceremony event for Dr. Martin Luther King on January 18. So we highly respect, the African American or the Africans or the people, minorities. So we have been doing all the event to with the minority speakers and to encourage minorities. So this is we honor. This is just a little history, Mr. Wilson, and this is a history of this Black History Month. So we highly honor and respect, and will continue to promote the professionalism among all the ethnic groups and the regions. So a few words about the AIAA. Is a great organization, the leading organization promoting aerospace. And once you join the membership online, you can immediately enjoy the AIAA Engage. You can chat with the member worldwide, post your question or resume or anything. You can start to network with professionals. And we regularly do events like today or different things to inspire people. Is for social networking, and doesn't really have has to be detailed technical discussion, but it's meant to inform and inspire people. So you can see our links there. And so this next Saturday we have exciting space architecture events, and then we have an event talking about people LGBTQ and minority gender, sex minorities in aerospace. And we have the anniversary for the first space shuttle and the space shuttle program. And we regularly do this event to inspire, encourage people to do a very good job, to get interested. And membership is an important part of the AIAA. And we have different type of membership. Educator, if you are STEM K-12 educator, is free. And this is the information of our membership chair, Aldo Martinez. And AIAA just announced the new high school membership, which is very exciting. It's free. So we are exploring the opportunities. So, our STEM K-12 outreach chair, who is responsible for, the classroom, school outreach, provide project, puzzle project or inspire student in classroom. So this Miss Khushbu Patel is our current outreach chair, K-12. And AIAA will also do national forum conferences. So we have aviation, propulsion, energy, defense, ascent is more for space, and the SciTech. And big digital pandemic, so the August forum is virtual. So there's just a couple of pictures, what we have been doing, with professionals, Mars landing, 2020 landing, the Raspberry Pi, and sustainable. This is a national level event with 2 AIAA fellow and several company leaders. And this was students, university students. Just give you a good idea to encourage. This is the event last week talking about building Hyperloop in California and also in space. So it's very exciting. Then we even talk about this is sci-fi series Space 99, the Eagles, how they participate in the moon or Mars space building. It's very exciting. And so today we are a great pleasure to have Mr. Stuart Maronway. He's a scientific director, Deep Time Technologies, and Tutume, Botswana. We were chatting, actually, the aerospace has been rapidly developing in Africa, and we're actually just chatting. The Rwanda has the CubeSat going to be launched, and the South Africa is a good program. He basically has a degree from in physics, and also he studied electrical and electronic engineering, and he specialized in quantum gravity, astrophysics. Very exciting. And he's going to share with us about this probing quantum gravity through astrophysical observation. He has been have very great experience in telemetry system as physics teacher, lecturer, research fellow, and now scientific director. So it's really, and you can see a lot of credential here, publications, and as we are, senior member always said, even for student, write up something and publish is a good thing. Especially for professional, it's a very important part of the life. So let's welcome Mr. Stuart Maronway for this great presentation today. Yeah, so it's yours.
Thank you, Ken.
Great pleasure.
Thank you, Ken, for that wonderful introduction. I would like also to thank the American Institute of Aeronautics and Astronautics, Los Angeles, Las Vegas, SEC, section for inviting me to give this talk on feasible warp speed from quantum gravity. It's an honor indeed. Thank you. I would also like to welcome the audience that is joining us for this talk. And I would like to inform them that this talk will include equations. These equations are important for us to understand the structure of space-time and how to manipulate it. So I'll try my best to explain these equations so that no one feels lost in the math. So our talk will be as follows. First, we will look into the historical context and motivation for warp speeds. Then we proceed to conceptual foundations of space-time gravity and the quantum vacuum. These concepts will help us build a theory of quantum gravity, which we will test with astrophysical observation. If we find these observations are in agreement with theory, we proceed to design feasible warp speeds from this quantum theory. I will later discuss about aerospace science and education in Africa, just brief about that. And then we go to questions. Right, so this talk is about feasible warp speeds.
Excuse me. Excuse me. Some attendee mentioned when you are not point out something on the slide, could you move the mouse away from the slide area?
Okay, thank you.
But if you are going to point out something, that's fine. But once you finish point out something, could you move it outside the slide?
All right, sure, no problem with that.
Thank you.
So at this moment in time, we could be asking ourselves, feasible warp speeds. Aren't these things supposed to be impossible given our current level of science and technology? Now, to answer a question about impossible tasks, we only need to look at some of our leaders in human history who have overcome seemingly impossible situations. People like Nelson Mandela. He's telling us from the past that it always seems impossible until it is done. We have also people like Martin Luther King, Rosa Parks, Mahatma Gandhi. We also have people like Albert Einstein and the founding fathers of the United States of America. So we ask ourselves, what do they all have in common that allowed them to overcome such impossible situations? Now, if we look closely, we will find that they were guided by a set of fundamental principles, which they called universal principles. And of course, they are imagined. For example, the founding fathers of the United States constructed the Constitution of the United States guided by a set of fundamental principles, which they called universal truths, and a vision of the new republic, which means they had a good imagination. So that is all what it takes to reach for the stars. A set of fundamental principles and a great imagination. So right now, let's ask ourselves, where are we coming from? Now, as early human communities, we survived on in situ resource utilization. That is, we survived off the land. And when these resources were depleted or harder to get, we simply had to migrate. Or we had to adapt, that is, to transform from hunter-gatherers into agricultural-based communities. As we built cities and villages, we had to mitigate, that is, we had to formulate rules and regulations on resource utilization. We also had to improve resource extraction technology. That is, we had to invent better hunting techniques, better farming techniques, better transport and communication technology. And this cycle was repeated over millennia: migration, adaptation, mitigation, improvements or advances in technology. And so where are we now? We are currently consuming our resources at a suicidal pace. The current rate of consumption requires at least 1.38 planets to remain sustainable. That's not all. If all countries were to elevate their consumption rates to the same rate as industrialized nations, we will need no less than 12 Earth-sized, 12 Earth-sized planets. These footprints can be calculated from a lot of carbon footprints calculated on the web. So we ask ourselves, where are we heading? And the answer to this question comes from none other than Carl Sagan, who tells us that all civilizations become either spacefaring or extinct. Now, extinction is not an option. So which means we are going interstellar. Now, interstellar has these challenges. The challenges of interstellar migration are deep space and deep time. Take, for instance, the nearest star system to us is Proxima Centauri, which is 4.2 light years away from the sun. It will take our current rocket technology based on chemicals at least 70,000 to 100,000 years to reach Proxima Centauri. And we are not guaranteed that we will find an Earth-sized planet there. And in order to find 12 Earth-like planets, we will need a larger region to scout, which means we'll need faster than light speed. But the laws of physics prohibit us from moving faster than light. But this has never deterred imaginative and creative people to find a way around the speed of light. For example, we have wormholes or Einstein-Rosen bridges. These were first proposed by Einstein and Rosen in 1935. Wormholes connect a distant section of the universe by a tunnel that exists in a hypothetical one-dimensional plane. So that is, for example, if I want to move from there, instead of moving right around this way, I can move directly through this tunnel. So that is the wormhole. They also require two black holes to be created. Another method is the Alcubierre type warp drive. Now, Alcubierre warp drives were proposed by Miguel Alcubierre in 1994 and further developed by others. This requires a means of placing a skip inside a bubble of flat space and stretching the space behind it while contracting the space in front. Superluminal speeds, that is speeds faster than light, can be achieved this way because space itself can move faster than the speed of light. But these proposals have problems. For example, wormholes are not practical. They require huge energy densities to create and exotic negative energies to keep them open. Possible since they will collapse when the spaceship tries to enter one. So this wormhole solution is not practical. We need practical solutions. We look at Alcubierre type warp drives. They are also not practical. The bubbles require huge energy densities to operate as well as negative energies. And to add further problems, they cannot be operated from within. You need to prefabricate a highway to operate a Alcubierre warp drive, which means you need another Alcubierre warp drive to create a Alcubierre warp drive, and that's not practical. It also does not explain exactly how superluminal velocities are achieved. Other researchers have tried to reduce the energy requirements, but still these Alcubierre type warp drives are not practical. Another notable feature about Alcubierre warp drives is that most people assume that general relativity is the final word on gravity. Yet it is well understood in physics that general relativity does not work well with quantum phenomena and predicts singularities. Now, once a theory predicts singularities, which means it's incomplete, it needs improvement. So what is needed is a technological revolution. How can we come up with a new technological revolution in aerospace? A technological revolution can only come up when we discover new laws of nature. Clearly, we need a deeper understanding of the fundamental structure of space-time, which can be found in a self-consistent theory of quantum gravity. To achieve this understanding, we need to start from our current well-tested theories of gravity, that is general relativity, and quantum field theory, and hope to find the nexus of these two pillars of modern physics. Now, in order to find the nexus, we need some clues. We can get clues from none other than Albert Einstein. Although he's not physically with us, his ideas and thoughts are still in our collective human conscience. He's telling us that space and time and gravitation have no separate existence from matter. Now, Albert Einstein was a person guided by principles. So this statement is coming from what is known as Mach's principle, which states that space-time can never have an existence without matter. In order for space to be there, there has to be matter. We are going to use this principle further on. So what is general relativity really? General relativity is the theory of gravity that describes gravity as a warping of space-time due to the presence of matter. So this is the equation that is describing this. This left side describes the curvature, and the right side describes the source of that curvature. So just like I said before, I will try to explain what each term here is trying to tell us. The first term is telling us about the curvature. The second term is trying to tell us about the stretching of space-time. The third term is telling us about an inherent energy inside space-time that causes it to stretch. We now currently call this dark energy. And this last term is the source of the curvature. It's called the stress energy momentum tensor. And in this case, it's the Earth that is curving the space-time, resulting in the moon orbiting around it. And those indices, mu and nu, they are just describing the components of space-time. The 0 is usually for time, and 1, 2, 3 are for the spatial dimension. So the Einstein equation can be reduced to this form. And we can interpret, and this term here can be reduced to an Einstein constant called kappa. So we can read the equation. For example, this equation is with zeros in the indices is referring to the slowing or increase in the passage of time due to the presence of energy and energy density, this energy density. And this equation, where this 0 refers to time and this 1 refers to a spatial dimension, is referring to the bending of time towards a spatial dimension due to the presence of an energy momentum density T01. Now, Einstein's equations are best understood in their vacuum form. Here we have removed stress energy momentum tensor, so this is empty space. So what Einstein's equations are telling us that straight lines in curved space-time meet, and this vacuum equation is called a de Sitter space, where this constant lambda is equal to this equation, where h sub 0 is Hubble's constant. Now, there's another concept that I need to introduce. It's called the Ricci flow, or best known as the Hamiltonian Ricci flow. It shows how the time evolution of the metric. What I mean by that is that how space-time evolves, how the expansion is evolving in time. And this is the equation. Now, I've circled this part of the conversion term. In most equations, you never find this. It took me some time to find this conversion term, because most physicists are interested in the structure of an equation. They are hardly interested sometimes they're not interested in the conversion coefficient. That's why they use natural units, where they reduce most of the constants to a value of 1. I had to work, if you find in my earlier publications, this conversion term is absent. I had to work about 3 years to find it. But once I found it, I found that it's easier actually to get. Basically, it's trying to tell us about that space-time is diffusing, it's a diffusion coefficient. Right, so with time, the Ricci flow is telling us that the separation between the object and their place of origin expands, and the space between the objects increases. So what are we saying in synthesis? Empty space is the zeta space and is associated with an energy we call dark energy. Now, let's recall from Marx's principle, okay? Marx was telling us that space-time is independent, cannot live an existence that is independent of matter. So this vacuum energy or mass is a charge associated with or generating the zeta space. It's just like a magnet is associated with a magnetic field. This energy density is associated with the space-time field. We shall call this quantum of energy that is associated with space-time the nexus graviton, because we are trying to look for the nexus between the concepts of general relativity and quantum field theory. So we can apply the uncertainty principle to find more properties about this. If we apply this equation from the uncertainty principle, we end up having force times space times time, delta t, delta x. This is the uncertainty in time, the uncertainty in space, or this is the space that is generated. Now, if this space, delta x, is the size of the Hubble radius, and this time, delta t, is the length of the Hubble time, we can reduce this part to this form. And then we can find the force associated with this space-time by reducing this the right-hand side to this form. We end up having force is equal to ma, which we know from Newton's law. So this implies that m is the mass of the graviton, which is the Planck constant times the Hubble constant divided by the speed of light squared. And the graviton-induced acceleration is the Hubble constant multiplied by the speed of light divided by 2 pi. Now, interestingly, this acceleration is equal to Milgrom's acceleration constant in Mond, which has been empirically observed in galaxies. So this is the hint that dark matter is also a manifestation of quantum gravity. So these are the hints that we are getting from what we have just understood from general relativity. And I've highlighted Marx's principle and the uncertainty principle to show that we are now being guided by principles in order to advance in our knowledge of quantum gravity. Now, let's look at quantum field theory. And one person to explain to us about quantum field theory would be Richard Feynman. He says that I think I can safely say nobody understands quantum mechanics. Now, what is he saying? Feynman is telling us that we understand the maths of quantum mechanics or quantum field theory, but we do not understand what it is actually telling us about reality. I think the problem stems from the fact that quantum mechanics itself was developed from mathematics. Unlike general relativity, which was guided by physical principles, quantum mechanics was guided by mathematics, and therefore it's now difficult to find interpretation of quantum mechanics. So what is quantum field theory? Quantum field theory describes matter and forces as a set of superimposed quantum fields whose values may vary from point to point. And crucially, this year is happening in flat space. It combined classical field theory, quantum mechanics, and special relativity. Particles and force quanta, that is packets of force, can be created and annihilated in a time governed by the uncertainty principle. It predicts strange phenomena such as quantum entanglement, in which two particles separated by light years can be affected. One can be affected by the observation of the other. It's a strange phenomenon that defies all logical explanation. Perhaps we might find the explanation in quantum gravity. As I said before, because quantum field theory was founded on mathematics, there are multiple interpretations of physical meaning of these equations. So we are still trying to find what is quantum field theory trying to tell to us. So this is one of the important equations in quantum mechanics. It is the Dirac equation of a fermion, that is particles of matter. Quantum mechanics describes the motion of subatomic particles in flat space-time as a traveling wave of probability. Already, this is a deviation from classical mechanics, because the classical mechanics is non-probabilistic in nature, especially when it's dealing with a single particle. But here we are finding that a particle is a probabilistic distribution. For example, in this case, a particle is described as a wave packet. And if you leave it somewhere, let's say stationary or nearly stationary, you'll find that with time, its probability, the probability of finding it where you left it is diminishing. And it can be found in a large section or at almost everywhere at once. So the other thing that is happening, the wave packet spreads out in space, delocalization, delocalizing in space in time. But could it be that its locality is expanding? Okay, it's not that the particle is moving in space, but it's the space itself that is expanding, diminishing the probability of finding the particle where you left it. The equation describing the time evolution of the wave packet is structurally identical to the Ricci flow that I mentioned earlier. It's also identical to the heat equation and to the diffusion equation. Now we come to the nexus paradigm. Now this is a preview of what to expect. An apple in extreme gravity would appear fuzzy according to the nexus paradigm. So we are now collecting the concepts that we have learned from general relativity and quantum field theory to come up with a quantum theory of gravity. Now, what we observe is that general relativity is preferably interpreted as a theory of straight lines in curved space-time. And yet, Einstein's field equation can also be interpreted as curved lines in flat space-time. By adopting this latter interpretation, we can start embarking on an alternative path to quantum gravity. Since quantum field theory is a theory built on flat space-time and as curved lines that appear sum over histories in the Feynman interpretation of quantum field theory. Moreover, the Ricci tensor in general relativity is the average of possible paths a test particle can take in a gravitational field. So we are seeing some similarities here, but now we are converting general relativity not from a curved space-time, but to a flat space-time in which there are no straight lines, but curved lines. So do we have evidence of a flat space-time? Yes. There are various independent observations by different research groups such as WMAP, Boomerang, Planck, and Boss that show that space-time is indeed flat. So let's start building the quantum theory of gravity. So we think of a flat space-time. Okay, so I've just chosen one dimension of that space-time. It could be time, it could be X, Y, or Z, but now we think of that dimension as an infinite line, okay? Now, in physics, there's nothing like infinity. Infinity is unphysical in physics. We don't use infinity. So this is meaningless to a physicist. We've got minus infinity that side and plus infinity on the right, and it has no physical meaning. So we tried the next step. Let's put a point in space. Do we have some physics from this? No, we don't have physics. Because to the left side, there's an infinite value, and to the right, there's still an infinite value. So it's still unphysical. Okay, let's try the next thing. Let's put a point next to that other point. Now we have physics, because we've got a gap between these 2 points that is measurable. It's called a gauge. We have a gauge, something that we can measure. So we are now in flat space-time. We have a difference between 2 points. We have a difference between these 2 points, and that is what we want to measure in physics. So we are in flat space-time, and in this space-time, which is called the Minkowski space, the Pythagoras theorem, the one that we know from high school, is written in this form. This in mathematics is called the inner product, but it's basically Pythagoras theorem. So this delta x or delta y are local coordinates, which means they are talking about this gap. We can now ignore these points because these points are not physical because they are zero. They are just marking boundaries of the local coordinates. Now, I look at the right-hand side of Pythagoras theorem in this part. I can split it into its roots in this form, okay? Now, in order for this right-hand side to be identical to this right-hand side, it means these coefficients that I placed must comply with the following rules. AB plus BA is equal to 0, and A squared is equal to B squared, which is identical to 1. Now, this behavior is called three-fold algebra. So we are in a space-time that follows rules of trifold algebra, okay? And it is found that these coefficients A, B, B, A are actually not coefficients, but matrices called Dirac matrices, and they obey this commutation rule, okay? And they show that they are in this parameter, shows that it's flat space-time. Another aspect of this space is that these local coordinates are endowed with a constant rotational motion and quantized spin. So what I'm saying is this, the local coordinates have a rotational motion that is associated with them and a spin associated with them, okay? Now let's look further into this gap. This is the measurement that we are taking. It is zero elsewhere, but there where we want it to be in the local coordinate. We can represent this as a pulse, okay? And a pulse can be represented using the Fourier integral. So this is a pulse of space-time which can be represented in a Fourier integral, okay? And this Fourier integral can be reduced to this for easier manipulation, where the coefficients, this coefficient here is reduced to this form, and we have this equation. We will give it, I'll tell you its name in a moment. So we also have this gauge that we found. This gauge cannot be like from minus infinity to plus infinity again. We need to have it have a maximum finite value. So we look to physics. Where can we get a natural large finite value of the dimension delta x? Or we find that the Hubble radius, we cannot measure anything beyond the Hubble radius. So which makes delta x the maximum radius of our space-time. And we also have to find a minimum, because if we reduce this gap to 0, we end up with a point again. It must have a minimum dimension. Now, a minimum dimension in physics is known. It is the Planck length. Below that, a black hole is formed. You can never measure anything. A black hole is formed below Planck length. So we can say the maximum dimension of our gauge is, of our local coordinates is the Hubble radius, and the minimum is the Planck length. Now, as I said before, that each of the local coordinates, or the local patch of space-time is associated with a spin. The Hubble radius, in this case, is associated with the spin, maximum spin speed of light. And if we note this value, which means the rotational speeds of smaller patches of space-time can be calculated from this form, which can be reduced via this translation into Hubble's law, okay? So what am I saying about this space? it is endowed with a spin, with a rotational motion. And you can calculate this rotational velocity using the Hubble law. And each local coordinate is quantized radii, okay? These radii, Rn, should be multiples of the Planck length. They can never be below, you can never have a value that is in between a Planck length. It must be multiples of a Planck length. So those wave functions that we alluded to earlier are called block energy eigenstate functions. They are globally and locally symmetric, okay? So this is part describes the local behavior, and this part describes the global behavior. Because these waves are confined to a locality, delta x, the wave vector, this value k, can only assume quantized values, okay? It can only assume quantized values, and the maximum is 10 to the power of 6. This 10 to the power of 6 comes from the ratio of the Hubble radius to the Planck length. Now, like we had said before, each local coordinate is supposed to be associated with an energy in it. And this is the conjugate momentum, okay? So this conjugate momentum is the energy of space itself, just like we learned about dark energy. This energy is in the form of what are known as virtual particles. So these are particles that appear and disappear in space according to Heisenberg's uncertainty principle, okay? Now, in this space-time that we have just found out, this law is a way of nature to borrow a fermion, a particle with half spin, okay? This is how nature borrows from the vacuum a particle with half spin. Now, if nature wants to borrow a boson, that is a force carrier, such as a photon, a W boson, a Z boson, a gluon, it uses this formula. We are usually familiar with this one, but this one is a new one where bosons, the space, nature itself borrows bosons using this formula. This one is stemming from the 4 components of space itself. So if it wants to borrow a graviton, which is a spin 2 particle, the spins are aligned up and the maximum value is 2h. 2 twice the minimum spin in nature. For particles such as gluons, photons, and W bosons, the spin is 1. All it needs is to one of the components to have this spin down, it will cancel out another one, and the net spin is 0. For bosons such as the Higgs, we need to have some components having the spin down, some having the spin up, such that the total spin is 0. Okay, so this is how nature is doing at a fundamental level. So what we are trying to do is to see what is happening at the fundamental level. We have found that there's a space-time that obeys Clifford algebra, and that the local coordinates or small displacement vectors, they are associated with a spin, and that each local coordinate is also associated with some momentum, which is inherent in space itself and comes from virtual particles. So now, if we want to calculate the energy of a graviton, we can simply use this formula. And knowing that the maximum radius is the Hubble radius, we can reduce the graviton for momentum, or the momentum that is associated with the graviton, into this equation. And we find that this part can be reduced into a form related to the cosmological constant that we found in the zeta space. And then we find that its final value is n squared lambda. So each local coordinate in space can be described by this term. And this term, we can input it in the vacuum equation, where we have the Einstein tensor. This describes something of this form. A packet of space, a spherical symmetric wave packet of space-time that has got virtual energy in it, that is generating a space-time. So what are we saying? We have virtual matter generating a packet of space-time. So this is dark matter. It is an intrinsic compactification of elements of space-time. And using the Ricci equation, we can see the time evolution of this wave packet. If it has high energies, it quickly extinguishes because n is very high. Imagine up to the values of 10 to the power 60 or 10 to the power 40, it quickly disappears. But the low energy ones, where n is small, they last longer. And we shall see later that they also have strong gravity. It will lead to what is known as asymptotic freedom in quantum gravity. So we have a high energy gravitons or high energy localities in space that quickly appear and disappear. But now, if in this theory or in this space-time, time can also assume negative values. If I put time negative here, this becomes positive, which means we can now have patches of space-time that expand. These patches must have their time in a negative direction. They will expand and generate what are known as dark voids. These are regions where space-time is expanding and particles of matter are pushed away from that space-time. So we can consider dark voids. These have been observed. They are there, and they don't have contain matter in them, or very few matter. They are the opposites of dark matter, in which the graviton time inside is positive, as a positive index. Now, dark energy arises from this patch of space, or the dark matter, emitting the ground state graviton, okay? And then we end up having the Einstein's vacuum equations in this form. Remember the old ones, the old Einstein vacuum equations, they didn't have this n squared, they had just this part only. Now we have added a term n squared minus 1, n squared, sorry, and this was the term before. Now we have included n squared. So what is happening here? The patches of space-time that are appearing, they borrow energy from the vacuum, but then they retain it in very small amounts they retain it using this minimum energy that they can. But as they donate this energy back to the vacuum, as they release this energy, they lower their energy state and expand, which means, like we saw previously, if the energy borrowed from the vacuum is less, the patch of space-time is larger. So whenever they return energy to the vacuum, they begin to expand. They expand, and this is they end up becoming up to the edge of the universe. They expand up to the size of the universe by releasing one graviton at a time, one minimum graviton at a time. Now, these are Einstein's vacuum equations. If we want to include the perturbations caused by the stress momentum tensor, then the full Einstein equations are this. So this is the full Einstein equation. Einstein equation was only missing this n squared. So what are we describing here? We are saying that space-time has got energy state from 1 to 10 to the power of 60. These are energy levels of space-time. Space-time is not just one fabric, but it's got energy levels. Now, these field equations, since we are dealing with flat space-time, these field equations can be interpreted as having curved lines in flat space-time. So what we are saying in this space-time that we are describing, nothing moves in a straight line, even in the absence of baronic matter, the matter that we see. Nothing moves in straight line in empty space. Everything moves in curved lines. So for the nexus graviton in the nth quantum state, this Einstein's equation can be given, we get this semi-classical solution for Einstein's equation for the graviton in the nth state. That is that patch of space-time in the nth quantum state. We get this solution. What is this solution telling us? That as n increases, this space-time becomes the curves in that space-time become straight. Remember, we were saying that this space-time, this flat space-time only has curved lines, but as the energy increases, the curved lines become straight. And as the energy is lowered, the curved lines become more curved until we get to n equal to 1. At n equal to 1, this is something strange happens. This graviton has a metric signature that is negative compared to the others, which means time in it moves in reverse. The space and time, they have got reversed roles. The time in this graviton is flowing negative. Now, what we are describing here as a dark matter can also be considered as a rich soliton. Now, this equation is called, this equation in mathematicians call it compact Einstein manifold. Okay, they are also called solitons or localized lumps of vacuum energy. That's what a soliton is. A localized lump of vacuum energy. And what does it do? It preserves its form while growing or diminishing, which means that sphere can maintain its shape when it expands or contracts. It preserves its speed and form after collision with another soliton. Now, this brings to mind what is happening in what is known as the bullet cluster, where two galactic clusters are colliding, and dark matter seems to pass through the ordinary matter and unchanged, really. And because it's a soliton, it preserves its speed and form after a collision with another soliton. Other features, this part where if I increase n to infinity and it comes straight, is called asymptotic freedom, which means at high energies, there's no curvature or strong gravity. So these high energy gravitons are actually straight lines, short straight lines, very short straight lines, like comparable to the Planck line, as you increase the energy. So as you increase the energies, they become straight, not curved world lines. So there's no strong gravity with high energy gravity. They don't exhibit gravity. Now this equation also shows that the value of n can only be 1, so there's no singularity, okay? And the ground state has a negative metric signature, okay? So the full Einstein equation that we found, where we include now the n squared, can be found in my works, that the solution to this equation is of this form, okay? So this part is now the Newton's part, Newton's law. Now this part is an acceleration induced by the graviton in the nth state. Remember, there's a rotational motion associated with a patch of space-time of a given dimension. There's a rotational motion associated with, and in this case is Bn. Now the last part is the rotational motion or an acceleration associated with dark energy, because it has the negative metric signature. It can't have a positive like the others who are above it. The n equal to 1 graviton has negative metric signature. So now we have Newton's law is now has these components. These components are hardly visible at solar systems level because the value of h is 10 to the power of minus 18. These components at local level in the solar system, you cannot observe this phenomenon. It needs sensitive instrument to detect this. So that's why Newton's law is valid in the local system, in the local solar system. But now non-Newtonian dynamics will start occurring when this part, you see the negative part and the Newtonian component, they cancel out. When GM over R squared is equal to HC over 2 pi. We end up the Weak field solution. This one reduces to this form, from which we obtain the following equation. These are equations of galactic cosmic evolution, because this cancellation of gravity and dark energy occurs at large scales, where the radius is large. So the first part shows us how space-time is expanding, okay? And I believe this formula solves the current Hubble tension. Because in this formula, the Hubble parameter, which is currently called the Hubble parameter, is actually a constant, and the expansion of space is dependent on these factors, on the mass in it. Which means R is dependent on the mass in it. The expansion of space depends on the amount of baronic matter that we know in it. And the speed, if you differentiate this equation to find the speed, we can also find the rotational speed at that radius Rn. And this is the rotational speed we find in galaxies, okay? This is the rotational speed we find in galaxies. And it is also called the baronic-Talley-Fisher relationship, which evolved. In my case, it's called the evolving baronic-Talley-Fisher relationship because of this term. But this term has been empirically observed in galaxies. Galaxies actually do obey this law. And we will show you later that they also need this term. And the expansion rate, by differentiating this, we can get the expansion rate of a galaxy. A galaxy also expands. And we can also have the expansion rate of the universe as well, using this formula. So we can place a cold dust cloud, that is a dust with low speed, okay? And then we can see that it will evolve in time because its locality is expanding according to this formula. And there we see a similarity with what was happening to a quantum particle when you leave it in a locality. It will also display the same features, okay? But now our time scale is in 100 million years, yet for a quantum particle is in nanoseconds, less than nanoseconds, far much below nanoseconds, okay? Now, we come to the full canonical quantization of general relativity, because we want quantum gravity is basically trying to rewrite general relativity in the language of quantum field theory, which is the wave function. So in my work, I have found that the metric coefficients can be reduced to this form, to those block energy eigenstate functions. So this is the metric coefficient, which can be written in this form. If you multiply these Dirac coefficients, it just gives you the Minkowski metric multiplied by this wave function. So the Ricci flow in these compact manifolds is in this form. Okay, we rewrite the Ricci flow in this form. Now this part here, I can reduce it to n-1 bracket multiplied by n+1. This part is telling me that there must be a covariant derivative acting on the metric coefficient and another contravariant derivative acting on this coefficient. So I'll reduce now substituting the wave functions for G. I'll get this part, the left side will look like this. And the right side, I have this covariant derivatives. One is contravariant, the other is covariant. And these derivatives are of this form. Okay, what is happening here is that we are seeing this is describing the time evolution of of what I was calling dark matter or a compact Einstein manifold. Okay, it's emitting. Here it's emitting a low energy gravity, the ground state gravity, and here there's an absorption of gravity. So what is the Ricci flow? What's happening here in the Ricci flow? It's telling us that space-time is coming from a high energy state to a low energy state. Okay, it's cooling down like a heat spot, a hot spot, as it cools down. So how is it cooling down? It's emitting a low energy graviton, so it's cooling down. Now, the most important thing is that term now, it appears here. And these terms, these are entangled derivatives, operators, sorry, quantum operators. These are entangled quantum operators. And this coefficient or term is the areal speed of the action of an entangled quantum operator, which is 17 square light years per second. So what I'm saying here is that this is the speed of quantum entanglement. Quantum entanglement involves quantum operators. When it operates on one particle, another particle separated by many light years feels the action, the operation of this operator, and the speed at which this operator, it acts over an area. It doesn't act in a straight line, it operates over an area. So it has an area of speed of 17 square light years per second. So this is what I wanted to explain about the expansion of space. So we start with the graviton with radius R1. It emits a low energy graviton, then it expands to R2. It emits a low energy graviton, then it expands to R3, and so forth. So a particle of matter, of ordinary matter inside it, will first it was at constant rotational motion, but as the emission of this graviton happens, it traces out a path that is curved like this, and it's called the geodesic. This is the path that it traces out. Now, if we include the presence of baronic matter, the matter that we see, we include this term, where n squared has this value. This is the mass maybe of the Earth or the Sun, okay? So what is this equation telling us? It's telling us that space-time is flowing towards matter. Matter is acting like a cold spot, and space-time itself is like a hot zone, okay? So the hot zone is flowing towards a cooler zone, okay? So now if you put a particle, a just particle of matter in this space, it will flow along with the space towards the massive object that is acting like a heat sink. So the reason why you fall is because space-time is flowing down like a conveyor belt, but accelerating as it goes towards the Earth. It's flowing with you towards the Earth, okay? We can also try to explain the wave function collapse mechanism from this theory. So before earlier on, we had said that if you leave a quantum particle, it will delocalize in space. It will spread out in space. So when you observe a particle, observation means inputting energy. So if you observe it for a time delta t, you're putting some energy delta E into it. So it elevates the particle, the space-time associated with that particle into a higher quantum state, and it shrinks because via this Ricci flow equation. It compactifies, it further compactifies itself, which we call collapse. Okay. And interestingly, these low quantum states, if you see my publications, these ones are in a low, high entropy state, and this one is in a low entropy state. So it's like you are reversing time if you add energy to this low energy space packet. You add energy, it reverses to its high energy state. All right, now let's start testing some of the equations that we found from the Nexus paradigm, the evolving Tariff-Fisher relationship, which I had earlier alluded to. So here, this part is called the baronic Tariff-Fisher relationship. It refers to this line. This is what astrophysicists and astronomers are using currently. They don't have these blue lines that are placed. Now, these blue lines are due to this term and this yellow line. So what is happening? For example, look at this galaxy here. It approximately has the same mass with this galaxy here, but its outer rotational speed for these two galaxies with the same mass, which means same physics must apply. Yet this one is rotating faster and this one is rotating slower, yet they are of the same mass. Okay? Why is this so? It's because of this term. Older galaxies will rotate faster than younger galaxies. So galaxies to the left of this red line are younger, and galaxies to the right of this red line are older and they rotate faster. Okay? So this is the evolving baronic Tariff-Fisher relationship. Now let's come to galaxy rotation curves. So I'm going to deal here with young galaxies where this term reduces to approximately 1, because time here, the time since the galaxy came into equilibrium is approximately 0. Okay, it's too young, it's a young galaxy. So this term becomes 1, which leaves this term to control the velocity. Okay, so if I can find the way stars are distribution in the galactic disk, I can calculate the speed at each level. Okay, now for this part here, I've assumed that the mass density is constant. Okay, if the mass density is constant, then I get this curve. And I compare it with this galaxy UGC 477. This is data from Kuzo de Nare, published in 2006 in Astrophysical Journal. I compare it with the data. You find that there's a correspondence, because but here I'm just using the average density, not the density that varies from different parts of the disk. Also for NG7, I get the same shape of this format. I'm just using this part. This is the part that is controlling this curve. And then do the same for this galaxy UGC 11820. I do the same for UGC 128, again using the data from Kuzo de Nare. And here I'm using that, I'm still using that assumption that the density is the uniform throughout the galactic disk. However, if I start varying the density according to brightness of stars along the disk, so there are some parts along the disk that are dense, some are light, you'll find that the curve follows the brightness of the stars, and the speed is almost exactly the same. This is also known as Renzo's rule, where these peaks are correlated with the brightness of that part of the galaxy. So if we now don't make that sweeping assumption that the density is uniform, but the varies are along the galactic disk, we find that the speeds exactly match each other. All right. Now there's the ring formation of Hoag's object. This is called Hoag's object, and the formation of that blue ring has always been a mystery. It has puzzled the mystery, and for 40 years, I think people have been battling over what is it. Now, the formation of this ring is due to the Lagrangian locus that occurs at this, when this happens, when the Newtonian acceleration is equal to the acceleration due to dark energy, okay? Due to that energy associated with the low quantum state of space-time. So when that happens, gas, it's called a Lagrangian point, where this is a place where the gravity pulling towards there and gravity pulling it away cancel out. So this is a Lagrangian locus where gas can settle. Okay, so this speed can be, the speed of the rotating ring can be found, and if we divide it by, if we square that speed and we divide it by the radius, we will find that exactly this value, the value that we calculated for the acceleration due to dark energy. This is the reason why these rings form, is because gas is accumulating, intergalactic gas is accumulating at a Lagrange locus, okay? It's accumulating at a Lagrange locus. We can also, we show that those dark matter, the compact Einstein manifolds that are in space, they can cause the bending of space-time according to this equation. You can constrain the value of the quantum number of space-time using gravitational lensing. So if I know the gravitational lensing, I can tell you what the state of space-time is, okay? And what will be the rotational speed of any object in that space-time. Now, galactic cluster, this is a Bell cluster where galaxies are colliding, okay? And this is showing the lensing effect. And these contours where scientists are trying to evaluate the mass of dark matter associated with the bending of light, okay? But now in the Nexus paradigm, these are compact Einstein manifolds that are interacting with each other, okay? So what am I saying here? This part here is hot and this part is cooler according to quantum gravity in terms of space-time, of energy of space-time. This part is more energetic and the outer parts are less energetic. But the less energetic parts, they make objects move faster, okay? They make objects rotate faster. So you can actually use it to solve what is known in gravity as the n-body problem. How? By modeling this or any interacting gravitational masses in terms of heat and applying the heat equation or the Ricci flow in this case to model the flow of space around. This will tell you how objects will move around in that space-time. So in order to solve the n-body problem in gravity, you have to model the whole region as a heat flow. And that will show you how object will flow in that heat, okay? Now, I would also like to tell you that the state of space-time, when you have baronic matter, that is the mass of the Earth, the value of n decreases as you increase matter. So which means the space-time in close proximity to a massive object is in a lower quantum state than space-time far away from it, okay? So let's look at another test of the Nexus paradigm. The Nexus paradigm of quantum gravity predicts that the event horizon telescope will observe this shadow of Sagittarius A star. You will have a dark spot, which is 26 micro arc seconds, and a wider circle, which is 4 times the size of the inner circle, okay? So the radius of this is 52 micro arc seconds, which means the diameter is 104, all right? And this is a tentative picture of Sagittarius A star, which was taken from the 2013 Event Horizon campaign, okay? If you look at this dark spot, it is actually 26 micro arc seconds. And the outer disk is approximately 104 micro arc seconds, okay? And here, this white line is a demarcation where general relativity predicted where this black spot would be, all right? So this is a tentative picture. We can't say this is the final picture, but then let's look at M87, what was observed in M87. And the picture was released in 2019, okay? So what we observed was this. This picture does not tell you much, but it tells you that there's a black ring and a glowing circle. Now, this analysis shows what is happening in that zone. If you look carefully here, you find that there's a black spot. This side of 0 is approximately 10 micro arc seconds, and this side is also approximately 10, okay? So this, if this is 10 and this is approximately 40, so the ratio of this inner circle to the outer circle is 1:4, just as predicted for this one, okay? The ratio of the inner circle to the outer circle is 1:4. So I can tell you that the Nexus paradigm is doing quite well for both Sagittarius A star and M87. Now let's turn to LIGO. Okay, LIGO is a gravitational observatory. It detects the gravitational waves coming from usually merging black holes. Okay, from these waveforms, they can find the speed at which the black holes merged. All right. Now, if we turn to the Nexus paradigm, okay, the quantum states next to the black hole, the black hole, inside the black hole, the quantum state is n=1. That's where the negative matrix signature is. Just outside the black hole, the quantum state is 2. And as you go on further, it becomes 3, 4, and 5, and so forth. So just outside the black hole, before black holes merge, they are in a n=2 quantum state. If I substitute 2 here, I get c²/4, or roughly a speed of half the speed of light. But we have to accommodate that there are some time-dependent perturbation that can slightly increase the speed. But so what we are saying is that when black holes are about to merge, the minimum speed should be half the speed of light, nothing less than that, but slightly more because of the time-dependent perturbation. So now let's look at the data from LIGO. Okay, these are the gravitational wave data that I've obtained, where they included this frequency. The other data does not have this. I couldn't find it, but from all those that I found this data, I found that the merging speed, the speed at the black holes, is 0.53, 0.54 of the speed of light, of course, 0.55, 0.52, 0.50. All of them are above half the speed of light. Okay, so which means this quantum theory of gravity should be on the right track, because so far we have found things that it is capable of explaining. Right, now we come to use this quantum theory to explain warp drives, okay? Now let's try to explain what is happening when an object is moving, all right? Especially this rocket. What is happening when rocket is accelerating? According to the Nexus paradigm, acceleration arises from the flow of space-time from a high energy state to a low energy state. Now, when a rocket is accelerating, the ignition point there where the gases are igniting, they increase the virtual photon density, okay? They increase the virtual photon density there at the point of ignition. This increase raises the quantum state of space-time. And this one here is not raised, which means it's in a low quantum state. Now, in a low quantum state, space, this is more curved than this. This is an exaggeration of the curvature. The space here above the ignition is more curved than the space within the ignition. So this space in a low quantum space, this state is contracted and is time dilated. But this space here is in a high quantum state. The space is dilated and the time is contracted. So this is how a rocket is accelerating. It's because of the local space-time flowing faster, not because the rocket is moving through space, but it is the space itself that is flowing faster, causing it's a local space, it's not a global space. It's the space associated with this rocket. Okay, so it's flowing. There's a flow of space from high energy to low energy levels. And it's like the Alcubierre drive, but without the flat part. Okay, this part space is expanded, this part space is contracted. So it's like the Alcubierre drive, but without the this rocket inside a flat system. Right, this happens on any motion, okay? A moving car, the rubber on your tires is pressing hard on the surface. And when it does that, the compression here increases the energy density of electromagnetic forces or virtual photons or in this part. So this part becomes high energy density. This space here is high energy density, and the space just in front of the point of contact is in a low quantum state. This part in a high quantum state. So space-time will flow, or an acceleration will take place. Space-time will flow from there to there in this locality, okay? Also in this locality. Same applies when you are moving. When you press hard against the surface, you are creating a region of high vacuum energy density, in this case using virtual photons. And the space in front of you is in a low quantum state, okay? So that's how you move. Your force arises and you are moved forward. Same when you are standing, this earth that you are, the ground that you are is standing on is compressed, is in a high virtual photon state. There are electromagnetic forces here that are that raise the state of the ground into a higher quantum state. It seems like the ground is now accelerating you upwards, because the part does not have compressed virtual photons is in a low quantum state. So it also happens when you are standing. So what are we saying? We are saying that the presence of extra vacuum excitations of the electromagnetic field elevates the energy state of the quantum, okay, vacuum, and the vacuum expectation value of the second quantum field. So if I want to calculate the average value of the electromagnetic force in that region, I use the electromagnetic tensor, okay? So if you increase the vacuum energy density by introducing more virtual photons in the impressed zone, the quantum state of space-time is elevated by additional states, okay? Remember that n squared here, we're just writing s squared times lambda. So the quantum state of that space is elevated due to the presence of above average electromagnetic field tensor, okay? So we can rewrite a Ricci solution in this form, okay? Instead, in terms of energy density or vacuum energy density, we can write it in terms of vacuum energy density. And this part is the solid. Yes, we can write the vacuum energy density in terms of the stress momentum of the electromagnetic tensor, sorry. And the inner product of the electromagnetic tensor is this. It's usually 0 for real electromagnetic field. This part, E squared minus E squared, usually cancels out. Because E is equal to CB. These ones cancel out. But in the vacuum, this, because they are virtual particles, the electric and magnetic fields are out of phase, suggesting that the vacuum can have the following condition of the invariant term. So B squared minus E squared over C can be greater than 0. It can be equal to 0, and it can be less than 0. Now this part becomes interesting. This less than 0 part, okay? So we can call this condition magnetic, null, or electric. So now we have another spaceship, okay? This spaceship generates an above average virtual photon zone around it, okay? And now we tune this zone to be electric. So which means the soliton, this zone, has this equation. Now notice that now there's a negative sign here because it's in the electric mode where we are neglecting the B contribution. So this is negative, it's negative, and this negative sign goes to the negative matrix, to the metric coefficient. So we end up having a negative metric. So we now have a space-like environment of negative metric signature in which the Ricci flow is faster than the speed of light, okay? So it's like space-time in this is flowing faster than the speed of light. But here it's because it's flowing in equally in all directions. This object may remain in we can say unstable equilibrium. Okay, so because it's flowing outward faster, the space-time here is flowing faster than the speed of light. We can use this equation. Okay, we can now express this equation for the Ricci flow of that soliton in this form. Okay, now this part of the equation is a condition for gravitational attenuation and reversal. If where this n squared is the gravitational field of the Earth, for example, if it's on Earth, okay, this n squared has to do with the gravitational field of Earth and at a radius r. So if this part here, this negative part, is larger than n squared lambda, then we have this object moving up. Okay. So what is it telling us? A negative metric signature simply tells you that time is moving like in reverse here. So while you fall towards the Earth, this thing falls upward because this time moves backwards. Okay. The covariant derivatives are of this form for this space-time. They can be placed in this, they can be described in this form. So what we are saying here is that we can control this field by changing the value of E, okay? So this will be called vector control or field orientation control. If you increase maybe the electric field this side, this object will move to the right. If you increase it this side, this object will move to the left, or any direction that you increase the negative electric field. But this electric field is virtual photons. It's not the real photon, sorry, but it is the electric field due to virtual photons. Okay, so what is happening? This object, this spaceship, is being elevated to a higher energy state of space-time relative to where you are, where a stationary observer is at. So what are we saying? It's like saying I've brought the space-time that is above the Earth, where the International Space Station is orbiting. If you bring that space-time and bring it to the Earth, that space-time has more energy than the one on the ground. Okay, so if you throw a stone at that patch of space that I've cut from high above the Earth and brought it to Earth intact, if you throw a stone at it, the stone must have enough potential energy to reach where that object, that space, that patch of space-time came from, that height. So it will encounter what is known as the gravitational potential U. That what I'm saying is this: if you take that patch of space from high above the Earth and bring it to the ground, you throw a stone at it, the stone will bounce back, it will slow down. Okay, it will slow down as it gets to that, because it needs to acquire the same gravitational potential energy as that patch of space is coming from. Only if you fire maybe a high caliber rocket at it, that's when it will slowly penetrate into the space-time, because it's got the gravitational potential well. In that space-time, clocks tick faster and space expands fast. Right, so from an observer, this is our spaceship, and this is the observer's timeline. We can look at what is happening between the observer who's outside the spaceship and the spaceship. The light cone is reversed. The spaceship's light cone is in the observer's past. Okay. What, like I said before, what it really means is that while the observer is falling to the ground, the spaceship is falling upward. So here is one experimental model of generating high energy virtual photons that we are working on at Deep Time Technology. So this is a technology that can elevate the quantum state of space-time. What it is missing currently is some nanotechnology components to increase the energy density of virtual photons around it. Okay, so that we can start testing this this idea of warping space-time or creating feasible warp drives. So we need some nanotechnology components that we have already designed to elevate the space-time around this object. Now, for the time being, we don't need to attenuate gravity to 0, 100%. Even if we could attenuate gravity by 10%, it would mean a lot to the aerospace industry. Just reducing the weight of gravity by just 10%, rockets will use less fuel, aeroplanes will use less fuel. If we could just imagine that, we would also help to save the climate, because we'll be expending less fuel. So all we need is to improve on this technology and attenuate, create the negative electric mode of the vacuum, of the electromagnetic vacuum. And then we can start attenuating space-time. So now I'll look at space science and education in Africa, okay? I'll just briefly talk about this. Africa is the fast and growing nascent space industry, having currently 20 countries with space agencies. The space agencies are involved in launching weather, communication, and remote sensing satellites. These agencies or space agencies, roughly we can say, started in 1998 when Egypt started sending satellites into space. So it's a very young space industry, but it is fast growing, okay? And also the growth is extending to university. We have students, these are students from University of KwaZulu-Natal who are designing rockets, okay? So their rocket has reached a maximum altitude of 18 kilometers. They designed it at school and they launched it into space. Currently, their record is 18 kilometers. So we have a huge talent of people who are interested in space engineering. We would also enjoy if people from your region in Los Angeles, where the space industry is very mature, to come and share the ideas with our students here in Africa. Okay, we also have universities that are dealing with space science, such as Stellenbosch University, University of Cape Town, KwaZulu-Natal. These ones specialize in space physics, satellite communications, and navigation and positioning. Fort Hare and University of Pretoria, they generally into astronomy and Earth observation. So this is briefly what I have to say on space science and education. The space science industry is very young, but it is fast growing, and investors are welcome to speed up the process. So finally, we asked the question. The question was asked by American Institute of Aeronautics and Astronautics, AIAA. If we don't take the challenge, who will? Right, thank you. We can now have questions and answers.
Yeah, great, fantastic. Yeah, I think we have attendee can't wait to ask questions. So we have Mr. Kumar Santosh. Let's see, where are you? Let's see, Santosh. We'll try to unmute him. Okay, go ahead, Santosh. You have a question.
Yes, I wonder if you could go back to the slide where you showed the waves on Earth with the spacecraft, with the dilation and the compression, real quick, because I have a question about that.
On feasible warp drives.
Yeah, it was the one where you showed the rocket with the time dilation or time compression and space dilation.
All right, I get that, this one. Let me share my screen. So we are talking about this slide.
Yes, if we go full screen real quick, so we can.
Kumar?
Yes, yeah, go full screen real quick because we and so I can take a better look at it here. If you go to the bottom right corner, there's the little tiny icon. The bottom right there, yeah, right next to the 100%. There's a slideshow button to go full screen. To the left. Go to the left of that. Left to the 100%. No, not that. Go to the there's a button that says slideshow next to that whole section.
Yes, I've gone to from here.
Yeah, that's fine. That'll work too.
Yeah, that's the one.
Okay, cool. This slide and the next slide. So go one more as well.
All right.
This one and the next one.
So I move on to the next slide.
Yeah, go.
Yeah.
Okay. Here. Is this similar to the compression shock waves and expansion waves and supersonic flight? Because it seems like a similar concept.
You see, in physics, there are symmetries in many phenomena. Sometimes, if we understand like the compression wave phenomenon, we can translate it and extrapolate some similar features. But I'm not very familiar with compression waves physics. But I can tell you what is happening here is just this part here, the space is expanded or it's in a high energy state, and the part in front of it is in a low energy state. And space-time, the local space-time here flows from generating an acceleration.
Are you familiar with supersonic flows? You know, like Bernoulli equation.
Yes, supersonic flow. Yes.
You know, and you know, once
Yes.
it goes, so you start converging a flow that results in shock waves. And you know.
Yes, creating a sonic boom.
Yeah, exactly. And then when you, but and conversely, and of course, you know, pressure, you know, all, you know, change correspondingly. And then when you, conversely, when you expand a flow divergently, it actually results in expansion waves and actually accelerates the flow even more. And so what I'm wondering is that a similar idea of what's going on here with the, I don't know what you want to call these, the gravitational waves or times or space-time waves, but is that
it's a flow of space-time from a high energy state to a low energy state. So of course you're right. It has to do with flow of waves as such. But like I was saying, I'm not familiar with compression wave dynamics. Okay, so I cannot make a very accurate description of what I can tell you is what is happening here in terms of my physics of space-time. Okay, but the point you're highlighting is what I was talking to Ken earlier about. If engineers come together, they start having more ideas on how to make the technology better.
Sure.
So if you have this, yes, that's what we are actually looking at, how to make it even more better. Okay, so this is the basics. What you are seeing here is the basics, but we could make it better because we have now understood why something moves.
Sure.
Okay, so we can now enhance that effect. So if you can use compression waves to enhance that effect, better. It will be another way of moving faster using minimum energy.
Is it kind of like a shock wave? That's kind of what I'm getting at.
Yes. Yeah, I like I was telling you, what I can tell you from my perspective is that it's a flow of space-time from a high energy level to a low energy level. That's as far as I can go. Making comparison with compression waves, I'm really, like I told you before, I'm not familiar with a lot of compression wave dynamics or physics. But if you are free to, we can even discuss it further if you have more ideas, we will discuss it further.
Well, I was just trying to find an analogy here. That's something that we could understand uh, uh, from fluid flows. You know, if you were to use a fluid flow
Yes,
analogy,
fluid
with,
flow,
with
yeah.
the concept of
Fluid
shock
flow, yeah.
waves, forth, would apply here as well because it looks somewhat similar.
Yeah, actually, I think you are getting it's very right. Well, now I'm getting the picture. This is the reason why you see that shock wave you are talking about. It's also like this is the reason why we have a light speed barrier. Okay, we have a sound
Sure.
barrier, and then which means we have a light speed barrier because of this effect that is related to shock wave compression. Exactly. Now I'm getting the picture. That's why objects can't travel faster than light because of that, what you're alluding to, because of the compression wave phenomenon. That's why objects can't travel faster than light. You can explain the why the speed of light is the limit because of those compression waves you are talking about. Thanks for that.
Yes, I knew there was some sort of an analogy there because when we had another AIAA presenter present in Long Beach, he was a Long Beach, he was a Cal State Long Beach professor, I think, or with the Oral Corporation. He actually just came up with propulsion technologies in which you could actually use gravitational waves to, for propulsion. And when you drew the diagrams, it looked exactly like aircraft going supersonic in terms of shock waves and expansion waves. So that's the reason why I wondered if it was the same similar concept.
Okay, that's another technology that uses gravitational waves. Now this one uses actually changing the metric of space-time using virtual photons.
Sure.
It doesn't use gravitational waves. It uses the technology that I'm describing for feasible warp speed uses virtual photons.
Sure.
To change the metric of space-time into a negative metric.
Very good. Thank you.
All right, thanks.
Yeah, but Santosh, I think basically what Stuart was talking about is to extract propulsion or energy from vacuum, which is different from using gravitational wave. So
Sure.
there's a fundamental difference that he's trying to tell. Then the other thing is, but what you say is kind of what from the Einstein was trying to do is, gravitational force. The planet moving, you can say is a force, like a propulsion pulled by the planetary body, but you can also view as Stuart showed, this curvature of space-time. So that's Einstein, which is a different view. He was trying to express this force is kind of curvature of space-time. So it's kind of similar, but it's not exactly the same. And what he's trying to do here is something new, is to extract things from, this is actually a hot topic. There are quite several groups that are trying to explore the energy dark matter. And this is actually better than the ocular drive or gravitational wave, because they are disadvantage of those, as I say, creating a lot of issue. You have to have something, behind you or something like that.
Now, the presentation that you hosted at Long Beach, remember with the Aero Corporation engineer?
Yeah, he actually spoke again 2 years ago in Palos Verdes library.
Yes. Now, what was he using gravitational waves, or was he using quantum gravity here?
No, he talked about possibly extracting vacuum, but he didn't elaborate on that. What he was talking is called a little bit like a faster than light technology, but he's not exactly trying to extract from the quantum vacuum.
I think I remember now. Basically, what he was showing was that when you start approaching the speed of light with propulsion technology, regardless of what the technology is, you will actually generate waves, like gravitational waves, analogous to shock waves. You'll call relativistic waves, I think is what the term he used. So you'll start kind of, as you start approaching higher speeds, that's very similar to a shock wave.
Yeah, I think that's, the gravitation, as Stuart was saying, is kind of long range, weak force. But I think he was trying to say here is at a quantum level, he's trying to combine the quantum, field and the gravity. So actually that came to my question, because I read something about this application of quantum gravity. They say they are most suitable, for the like a boundary of the black hole. And there's a kind of layer that this apply very well. Or this actually apply everywhere? That's actually my question. Is it applied everywhere in the universe, or is more significant, a certain area?
When I say the boundary, do you mean like the event horizon?
Yeah. Yeah, so actually I have this question, so but from the speaker's talk, it seems that this is fundamentally everywhere. So that's actually initially I have a thought when I was thinking is that you approach some kind of black hole or wormhole, then utilize the quantum gravity, then you can kind of achieve this this kind of propulsion. But if it's he talked about the rotation speed of the galaxy as evidence of this quantum gravity theory. So then I'm kind of, can you use this as a general propulsion? If we can benefit from the quantum vacuum everywhere, or it has to be more close to kind of black hole? So how do you think, Mr. Maroney, how do you think? So can we utilize benefit everywhere in the universe for this kind of quantum vacuum, or it's better to use it in a near black hole, or something very with huge mass?
All right, okay. In my physics, my research in this phenomenon of black holes, the zone near a black hole is in a low quantum state, which means if you put a particle of matter in that zone, it's fuzzy, just like I showed that apple. It becomes fuzzy, it becomes delocalized. What I was trying to explain in this presentation is that the best way is not to use concepts such as black holes, and we can use virtual photons. We can use virtual photons. We just need to generate virtual photons, not black holes, like for wormholes. All we need are virtual photons, an elevated state of virtual photons. Yeah.
I see. Yeah, so somehow the spacecraft
so that's why it makes it feasible. That's why it makes it feasible, because we are not using long-term concepts such as black holes. We are using something that if we can improve on generation of virtual photons, just surround a spaceship with a zone of high level of virtual photons in the electric mode, they will switch the space-time metric and attenuate gravity, like I showed in that equation for attenuating gravity.
Yeah, so it can be applied everywhere. Yeah, as long as you can generate the virtual photon density gradient.
Yes. So we are saying this equation here, this part of this equation, this refers to the contribution of the Earth's gravitational field. If you make this part negative, more negative than this part, then this object will fall upwards. Okay? But we don't necessarily have to make it more negative than this side. If we could just reduce it by even 10%, we could make huge savings on fuel, on launch facilities. So all we need is to start incremental steps by attenuating the field using this equation. What we need are virtual photon states, high energy photons, to attenuate the local gravitational field.
Very good. I think Mark asked a question. Can you see the Q&A box?
Yes, yes.
Yeah, Mark Schneider, Mr. Schneider asked a question about Einstein barrier.
All right.
Did you see it?
Yes, I understand. Like we are saying, this is nothing to do. You see, Einstein barrier is conceived when an object is moving in space. Now here, it is the space-time metric that is moving. Okay, is this local space, you see this sphere, it is the local space metric, the local space that is moving, not the spaceship. So space can move faster. But now this one is in a negative metric state. Basically what it's telling you is that it falls opposite to normal matter. While normal matter falls, matter outside the metric, that is matter outside the metric will fall down to the earth. This one will be repelled by the earth. But you can increase the repulsion effect or the flow, the Ricci flow inside, the negative Ricci flow, by . this is not for real photons, it's for virtual photons, photons that emanate inside the quantum vacuum. Remember, space-time is related, it is related more to the virtual photons that are creating it. So this part, if you could elevate this part, you don't even have to have a, you see, okay, let me even make it much more clearer. What Schneider is talking about, if you are accelerating an object from below the speed of light, okay? But this one is like it's in a reference frame that is in where it is slower than the person outside it, okay? What am I saying? It's like things around it are moving faster than it. Itself is it's not moving inside itself, it's not moving. When an object is not moving, it has a maximum speed of the speed of light, okay? When an object is stationary in space, it has a speed in time equal to the speed of light. So this object is not starting from below C, it's starting from the speed of light in time, if I have to put it that way.
Yeah, I think maybe you can correct me. I think, Mark, I think this is kind of different kind of way of thinking. For example, some people can draw the 2 points at the end of both end of the paper. If you want to draw a line in trouble, then you have kind of the regular propulsion thing. But if you fold the paper, to put these 2 points together, that's folding the, the space-time. So in a sense, I think it's changing the, the space-time around the spacecraft, but it's not actually try to propulsion for the spacecraft. You see, you fold the paper from both ends, and then you can touch the 2 points together without moving the dot, right? I think that's kind of things like that, something like that.
Yes, what you are doing is this. In my construction, you are actually elevating the state of that space way above. See, the energy state of that is way above where that observer outside the spaceship is. The space-time is in a higher energy state. Okay, it's in a higher energy state there than for the person who's on the ground. So here we are talking in quantum gravity. It's better to talk in terms of quantum states of space-time, not in terms of curvature. So
I see.
this space, yes. So we need to shift. That's why it's the Nexus paradigm. We need to shift our view of gravity from the geometric view of Einstein. Yes, it works well, but I believe from what I was showing you the evidence for the Nexus paradigm, it's better off to go into the quantum gravity zone. In this level, it's better to discuss space-time in terms of energy states. So that spaceship is in a higher energy state. It's like a bubble of high energy, okay? Which once, let's suppose I create the space-time around the spaceship to the same energy density as the space-time around the International Space Station. This object will float up to that level, okay? It will be repelled up to the height of the space station without expelling, because this space-time wants to be in a state where it's equal to where it's in the same state with the others. Are we together? It's being elevated upwards. Space state is the quantum state of the space around the spaceship is the same as the quantum state of an object far away from the gravitational field.
Yeah, I see what it is. So you change by changing the level of the quantum gravity state. It happened that the spacecraft can be in a different space-time by changing the state.
Yes.
Yeah. Okay.
So it's like reversing the flow of water. Okay, it's flowing. For an object falling to the earth, the flow is going from above the earth to the earth. But in this case now, the flow is going from the earth to away from the earth. The flow, the rich flow. Okay, it's like you have created this curved zone might represent a cold spot, but now you have created a hot spot in the middle of cold spot, okay? So this is what is happening. The space time around the spaceship is in a higher energy state.
Okay, very good. I think there's another question from Mark. Did you see that? About the warp bubble.
Yes, in a way we can call it a warp bubble. We can call it a warp bubble, but like I was saying, quantum, it's a bubble of more. Hello?
Hello, can you hear me?
Yes, yes, we had lost internet connection.
Okay. It's okay now?
Yes, it's okay now.
Go ahead.
So, yes, what I'm saying is that these are different concepts from the geometric concept in general relativity. We are better off talking in terms of energy state of space-time. That is, what energy state of space-time is the spaceship in. But this spaceship generates a negative metric signature. That's the most important thing, because it makes it fall upward, that basically.
Hello?
The ground itself, it falls away from the ground because of the negative metric.
Okay. Hello, can you hear me?
I can hear you.
Oh, okay. So maybe Stuart, internet over there is kind of unstable.
Yes, let me switch on to another network. This one is becoming unstable.
Yeah, try not to show the slide because you already show it and that might affect your speed over there. Is okay? Mr. Maronway is okay now? All right, looks like we might have, yeah, he said he's trying to switch to a different network. So during this time, I think I would just try to start the second one, and then when he rejoin, you're welcome to speak anything. Okay, so let me do this. So I'm going to say a little bit about the quantum computer, quantum supremacy. We have been trying to kind of set up the event and in the past 3-4 years, so I gather some kind of information. They have a background in, in the related field. Although I was not doing quantum computing, but because I was information and I have actually studied, quantum mechanics and the quantum field a little bit, and been kind of extensively exposed in computers. So I'm trying to provide you some basic information. We are going to have more events with quantum computers, and I've obtained my PhD from Carnegie Mellon University in around 2001, slightly after September 11th. Okay, so I'm just self-introduced myself. So I think the speaker is back. So let me switch back to him. So Mr. Marui, can you hear me?
Hello.
Yeah,
Yes,
please.
I hear you.
Good.
All right.
So yeah, you continue your explanation.
All right, sure. All right, what I was saying is that this reason why I'm saying it's a feasible warp drive is that all we just need to do is generate a virtual photon states around a spaceship. Okay, if you generate these virtual photon states in the electric mode, they will generate a negative matrix signal. So this is not far out like trying to create a black hole. All right. So the virtual photons in the negative, in the electric mode, they act actually like the negative energy that our Cuvier is looking for. Maybe that makes it clearer. The electric mode of the virtual photons acts like Cuvier's negative or energy. Okay, I don't know if there's any other question.
So Mark, Mr. Schneider, is this okay? If you have further questions, you're welcome to speak out. Okay, so if Mark has,
yeah, I'm
okay.
here. Yeah.
Yeah, is this a speaker's explanation okay for you, or you have further question?
Well, it's to develop a warp bubble around the ship. Wouldn't you have to have some kind of a technology to create the bubble? Like an electromagnetic field or or something like that. How would you create this warp bubble?
All right. What I was, this is the technology that I'm working on, but I will not describe the details of the technology because of patenting process, okay? What I'm saying, you can actually generate a virtual photon field around this apparatus of negative electric mode. And what we would want to measure is an attenuation of the gravitational field, not necessarily 100% cancellation, but an attenuation using some nanotechnology components that we can add onto this device so that we attenuate the field. So you don't need exotic technology. The nanotechnology components can be manufactured, it's just that they are very expensive. They can be manufactured and we can test because it stems from the theory that we've tested using astrophysical observation. And we find that it's working well. So we can also test this theory using this equipment to see if can we make a cancellation of gravity or even attenuate it to some percentage. Even if we were able to attenuate it by 10%, that would be fantastic for technology.
Okay, good. Well, I'm glad to see, Stuart, I'm glad to see you're working on a technology to create the bubble. So that's what I was, yeah, thank you very much for pointing this out. Thank you.
Sure. By the way, it's called stimulated quantum vacuum activity.
Yeah, Squaba.
Wow, yes.
Very
It
good.
come down back it elevates the average value of the electromagnetic tensor for the vacuum electromagnetic field.
Yeah, so keep us updated. So when you have some progress, come back, or anytime. It doesn't have to have
Sure,
any
sure.
progress. Next time when you have something, you come back and
All right.
tell us, what you new design or what you plan to do, or you got the nanoparticle. Tell us the great news. Have
right.
some, yeah. And great to see
Sure.
your great progress and all the wonderful development in Africa. It's wonderful.
Okay.
So we'll stay attention. As I said, we'll have an article this month or next month, about the development over there. All right.
That would be great.
Yeah, wonderful, wonderful. So thank you so much again, Mr. Moroni. This is fantastic, wonderful, very exciting. And people are paying a lot of attention now. Yeah, very good, very good. Yeah. So so as I said previously, next kind of talk is kind of discussion because we have been trying to find speakers for the quantum computer, but it's kind of keep always delay. So, but it's been 3 or 4 years, so I feel this is a good time because Stuart is talking about this quantum, and this quantum thing has getting into aerospace, and I'm just trying to tell you what I saw, heard, and from the around the people and the news and how this quantum going to affect aerospace and how it's going to how we should be informed. So I think it's a great opportunity. And if anything, please correct me. But this it means for a discussion. It's not really meant for a kind of authoritarian for authority talk, but it just give you the information I gather. And in the process, trying to set up the good program for AIAA Los Angeles Las Vegas section. And you see I heard a lot of news, China trying to do something, those kind of things. So I try to also clarify those myths and those kind of things. And this is highly related to Mr. Moroni was talking about. He already talked about the quantum entanglement, and he also talked about Schrodinger equations, those things. In this discussion, it's not going to have a lot of equations, but it's going to show you some of these. The intention is to kick off the program for AIAA Los Angeles Las Vegas section, as we might have the speaker very soon, on this topic, or depending on the process. So basically, there's a lot of topic here, but just to show you, it is an exciting topic, and many companies like IBM, Google, Microsoft, Lockheed Martin, they are putting a lot of money and effort into this. So we want to see what's going on. So in this page, you see IBM Q is they are doing the superconductor, quantum computer, and there's a D wave. They're also doing, superconducting, things. For IBM, they're doing the Josephson junction, those kind of stuff. So just try to kind of mention, for this talk, this discussion, it is not intended to sell any company product, and it's just intended to let people know this is something emerging as important for aerospace, and it's also have fun, and also to people got interest, and we have had more discussion on this and events coming up. I just feel that we cannot wait. This is very important. Okay, so this is something coming up from the news. There's a company called the D-Wave System, and they have been working on the quantum computers and working with Lockheed Martin. Oh, Santosh.
Yeah, when you're not or not pointing at the, if you can move the mouse cursor off the screen. So
okay. Okay. Yeah, so you can see that they are working with the major players. Lockheed Martin is a very important player in this, and they work with USC. That's another very big aerospace research center, and Los Alamos National Laboratory. They work on various things from nuclear engine from defense aerospace. So just to show you, of course, there are other companies, regular computer company and internet company or financial companies. Okay, so I think Stuart mentioned is gentleman is Richard Feynman, and he's actually quite important in this regard, and he is actually connected with aerospace very well. And he won the Nobel Prize 1965, quantum field theory, quantum electrodynamics. And He actually, in 1959, he already said something, because there's such a smaller scale, it suggests might be exported in the design more powerful computers. And what mostly people are talking about is 1982, that he proposed that because the nature is actually composed of things better explained by quantum mechanics, not by classical physical mechanics. So he, in this occasion related to IBM, then he felt that there's a great possibility you can build a computer using quantum mechanics and to simulate nature. This is in 1982. That's very well regarded. And I want to play a short is by Bill Gates, a kind of review about Richard Feynman. So let's just see if it plays well. I will share.
Hit the full screen button when you can.
Okay, yeah, it's loading, so I'm waiting for its loading.
Well, Richard Feynman was an incredible scientist, but perhaps even more importantly, he was an amazing teacher. I'd read the Feynman lectures on physics. I learned a lot of the physics I know from that book. He could explain things in a fun and interesting way to anyone.
Things happen that don't happen the other way. You drop a cup and it breaks. And you can sit there a long time waiting for the pieces to come together, come back into your hand.
Cornell invites him to give this series of lectures. And it's Feynman explaining physics to non-physics majors. It's so good. And for me, those are the best sort of general audience thing that Feynman ever did. So I've always recommended those lectures. I helped get them up on the internet. And because he had pushed himself to have such a deep understanding, his ability to take you through complicated things was incredible. And he's the only one who's really succeeded in explaining quantum physics in a clear way. Taking something that is a little mysterious to most people and using very simple concepts to explain how it works. Well, that's classic Feynman. He made science so fascinating. He reminded us how much fun it is and how there really are answers. He's such a joyful example of how we'd all like to learn and think about things.
It's a very interesting thing, this tremendous world of interconnecting hierarchies. We are gradually understanding this connection, proving all the time our understanding of the world.
Okay, so basically this is Hardis, and his major contribution is in the quantum electrodynamics, but he is a figure. He played drums. He was talking about computers, a different kind of thing. Very, people really like him. We'll talk about his connection with aerospace shortly, but in the real world, what he was trying to say, like proteins or molecule. This is a fertilizer that IBM trying to use their best supercomputer summit to resolve, but they reach a bottleneck because in order to accurately simulate nature, you need to kind of represent each of the electrons and each molecule and the simulate the distance, the forces, etc. That's just very tremendous, huge work for even the fastest supercomputer we have these days. It's very difficult. We can do a very small molecule. So this is one of the bottlenecks we are facing right now. Sorry. And so this is picture, try to connect with what Stuart was talking about. So there's, quantum mechanics and the general relativity. You can see people are trying to build spacecraft to study the gravity. And you can see the chart here, the relationship between Newtonian gravity, classical mechanics, and quantum field theory, general relativity, and the quantum gravity. That's position where Stuart was talking about. try to grant it. So you basically have quantum electrodynamics, which is part of quantum field theory. The reason why I mentioned is just try to link, from the previous talk to this one. So now I'm going to talk about Richard Feynman is actually very important in the aerospace because the challenger, he was very well known for the challengers. He was in the Rogers committee. And the committee, the vice chairman was actually our well-known Neil Armstrong. So let me play a short clip, to let you see what it is. I won't play the whole video, just to show you what was the committee was all about.
And our criteria, since all of the rain protection modifications were not in place, that after each rain, we would go out and re-inspect the water protection system, which is sprayed on the tile.
Yeah, this is Sally Ride, the first American woman in space. And now I'll roll back.
Maximum expected flight pressure. And what that amounts to is that's 8% of the 1.4 safety factor, and that's the convention in solid rocket motor technology.
Excuse me, on what do you apply this?
This is Neil Armstrong.
112% proof test?
Segments.
You can see Richard Feynman was sitting on the back side.
Segment.
Each segment.
Thank you.
Does the term limit load apply to the ultimate strength of the material or the yield point or what?
That's ultimate. That would be ultimate, and that would be breaking up. The requirement is that you don't break up at less than 1.4 times the maximum expected load. You don't have an ultimate failure.
Right. Thank you.
Then we have done X-ray, and we did 100% X-ray of the propellant in the first 68 segments that were manufactured.
So I'm going to play another one. This is more directly on Richard Feynman. This plays a very important role in the...
Good evening. Here's what's happening. The report on the space shuttle disaster is now in President Reagan's hands, and the public will get a look at it on Monday. Tonight, CNN's John Holloman reports some hard-fought battles among members of the investigative commission that wrote the report. One member was harshly critical of NASA, and therein lies the tale that John Holloman unfolds now from Washington.
Commission member Richard Feynman charged that NASA had virtually ignored the principles of physics and good scientific practice in designing, testing, and building the space shuttle. The Nobel Prize-winning physicist wrote a section of the final report known as Chapter F. Commission sources say Chairman William Rogers read the chapter and was furious. He called Feynman to Washington Wednesday and urged him to tone down his criticism of NASA because Chapter F threatened to destroy public confidence in the space agency. Feynman returned to his home in California and began his rewrite, but then changed his mind. Sources close to the scientist say he felt his ethics were being compromised. He sent a message to Rogers threatening to resign from the commission and demanding his name be taken off the final report if his chapter was not included in its entirety. After a day of tense negotiation, Feynman agreed to stay on the commission and sign the final document.
But the result of all this is that President Reagan will not read Dr. Feynman's criticism this weekend at Camp David. His chapter will be printed and released as part of the lengthy appendix to the report. At the White House, a senior administration official says there's still no consensus on a fourth shuttle orbiter, but CNN has learned the president does support the plan to replace Challenger. The senior official says if the fourth orbiter is approved, the president will ask Congress to appropriate money to build it rather than take money from current NASA programs. John Holloman, CNN, Washington.
The members' one promises to be somewhat more harsh in its evaluation of the space agency than the General Commission report being made public today. Sources close to the panel say the Nobel physicist Richard Feynman had concluded that the chances of a catastrophic shuttle accident were far greater than NASA had predicted before the Challenger disaster did happen. Dr. Feynman, you may remember, was one of the more skeptical members of the Rogers Commission. He had asked some of the tougher questions of the NASA witnesses. In fact, he had threatened not to sign the final report out today because it was, he thought, not tough enough.
The Nobel Prize-winning physicist from the California Institute of Technology. Welcome, sir. Was this an accident that did not have to happen?
Yes, it was. It was an accident that had many, many warnings that there was something wrong and that it might sooner or later go off. And the warnings were disregarded.
Disregarded out of incompetence, out of a faulty system, out of bad judgment, for what reason?
I had some difficulty with that. I kind of imagine that something like a child that runs in the road, and the parent is very upset and says it's very dangerous. And the child comes back and says, but nothing happened. And he runs out in the road again several times, and the parent keeps saying it's dangerous, and nothing happens. If the child's view that nothing happened is a clue that there was nothing going to happen, then that's going to be an accident. You could hear.
Okay, so I guess this, let's see.
Brake squealing.
This is another one. I'll just try to build a link between him and the aerospace and the quantum computer in aerospace.
Before the event, from information that was available and understanding that was available, was it fully appreciated everywhere that this seal would become unsatisfactory at some temperature, and was there some sort of a suggestion of a temperature at which the SRB, I guess you call it,
yes,
shouldn't be run?
Yes, sir. There was a suggestion of that. To answer the first question, given the configuration that we were in, that the seal would function at that temperature. That was the final judgment.
But Commission member Richard Feynman, after examining the O-ring, had a surprise.
Oh, I took this stuff that I got out of your seal, and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
Okay, so I'm coming back so just try to connect this, and it's a very important time and tragedy at that point. Okay, so this is, if you look at around the aerospace companies, this is one from Aerospace Corporation. It's very interesting. They were actually suddenly moving into, doing quantum communication for space. They do a lot of satellite, so there's a lot of effort in this. And another one, they are doing the unlocking quantum key distribution, for space as a cybersecurity. It's very important, for space communication and also the local aerospace cybersecurity. And you can see in the news media, this is a very recent one, just February, is that China launched a cloud-based quantum computing operating system software to challenge US in technology. It's kind of scary, this what's going on. Then you see this, back in 2015, when China sent the laser beam to space, they created the entangled state and kind of proved the teleportation can be said. This, people say, okay, now China can do Star Trek, those kind of thing, and can do quantum internet. Some people got scared, but exactly, it's really like that. They can beam people into space. It's not exactly that, but you will see later on. Then you can see Chinese scientists set a record for the farthest quantum teleportation. I believe 870 miles. This is things like this keep going, and people say, even space.com scientists, you can do beam people up, so some members attendee came to me and they say, what's going on? And we're trying to find speaker to explain all this. And again, you can see this quantum computation, teleportation, 300 miles, those things. And Northrop Grumman, this is Northrop Grumman website. They're citing this quantum entanglement and teleportation, this sci-fi technology in real life. They're actually citing the Chinese, scientists experiment on this. So there are a lot of hypes, or things there, and is any fact or any exaggeration there. Now people saying, those entanglement teleportation may be violate the principle, the maximum speed of light, but actually it doesn't. You as well see later on, and also Stewart also explained a little bit, but it's not like that. It's just transporting the information, the state of the photon, so it's not actually exactly the mass, that or energy that being transferred. And another thing is, you will see later on, quantum computer is not going to replace the classical computer. It's going to be working together. And it's not immediately it's available, but it's not immediately everybody need to use it. In the next 10 or 20 years, you will see this very critical stage for quantum computer. If it works out well, yes, maybe in 20, 30 years, 50 years now, it's very popular. But keep in mind, a lot of exaggeration. For example, actually, Feynman was talking about the space shuttle. He feel the problem was that it promised too much. You can run for 60 missions, reusable. If you promise too much, even though the best technology or a great idea, sometimes, you got some kind of setback. So we also have to be careful about this. And the cold fusion case that we heard, the claim too much, and it's also come to hurt the technology itself. Okay, so there's the issue of quantum supremacy. That's basically excited news. Google Sycamore quantum processor a few years ago in 2017 first, and 2019, they achieved a test of 200 seconds. And then they published the result in Nature, which is a very prestigious scientific publication. They claim that they achieved the computation speed much faster. That would take 10,000 years for the state-of-the-art supercomputer. Then, of course, Santosh, you have any question? Well, anyway, if any question, just let me know. Okay, so what happened is, but it's there's a lot of myths over there. So, for example, IBM came back to claim that it's actually not true, because you pick the right algorithm. They can actually do using the Summit, the fastest supercomputer, and solve the problem 2.5 days. So when you ask around, the field for expert doing, they are very careful about saying quantum supremacy. And the quantum supremacy is actually not saying China is dominating the world. It was actually talking about versus the classical computer, when the quantum computer will reach the supremacy over the classical computers. But you have to be very careful, because it heavily depends on the algorithm you use. So if you change algorithm, change the problem, it might not show the significant result. Then in 2020, the Chinese Science Technology Institute achieved another one, 76 qubits. Okay, Santosh trying to say something. I think you can unmute yourself if you want.
Yes, I did. Before we go into any more detail of this stuff, you may want to just describe what a quantum computer is. For example, some of the things that I have heard is that the reason it's called a quantum computer is that, and maybe you can say if this is true or not, is that instead of using voltages for ones and zeros for high voltage, low, that they're using the quantum number electron spin plus a half and minus a half as a logical 1 and 0. And the other thing is that the superposition principle, that the main advantage being that you can allow for multiple computations to all occur in parallel as opposed to doing it sequentially. Those are two things that I've heard about quantum computing. So you want to describe what a quantum computer actually is before we go into it, so that people understand what this actually means.
Yeah, actually, what you're talking about, actually, I'm trying to put it a little bit later. But since you mentioned, I just pointed out, because to go to this stage, there are a lot of things you need, not a lot, there's several things you need to go through before you reach this. But what Santosh said was true. Classically, in computer, you have the classical bit 0 or 1. So each time is either 1 or 0. But for quantum computer, as Santosh said, is represented by a sphere, and because the natural quantum mechanics, you can be a superposition of 0 and 1. So it's in this picture. I think that's probably what Santosh was talking about. So the advantage of quantum computer is it can, it doesn't have to be just 1 or 0. It can be a combination, or say superposition of 0 and 1. So in this case, 0 represented by up and spin up, and 1 state means spin down. I'll explain it later. So if you have 3 qubits, then you can see you have 8 states simultaneously. So this is like a parallel computer. So if you can achieve, the superposition is a very important feature because of this, versus the classical computer, you can only have 1 or 0 at one time. And this you can have, multi-dex 3 qubit has 8 already, and you can achieve superposition and entanglement. And this is exponential. So they always like to use a story of the chess player as the king, for 64 square on the chessboard. And the first day is 1 grain of rice, and then gradually it was just too many, like a Himalaya mountain. So the quantum supremacy will be achieved mostly for the n. You have a qubit number over 50, mostly like 64 or something. You start to see the effect. So this is what it is all about. So let's see. But to understand this, oh, sorry, I moved the cursor away. So but in order to understand this, you have to go through a little bit background. But since you mentioned it, it's a good idea to mention this, the importance of bits, qubits, superposition. And another 2 important concepts is entanglement and interference, which means measurement or noise. These are the key differences. But this is a very big difference between quantum computer and the classical computer, because it's like a parallelism. Then you can have the state simultaneously processing it, and versus the classical computer, when you double the number from 32 bits, 8 bits, 16, 32, 64, 124, 256, and you see it's double, triple, but you don't see the exponential capability. But there's come with some kind of price and limitation, which we'll talk about later. So I'm going to go back a little bit. So there are many slides, but I just some of them just try to go through very quickly. Where are we? Okay. Okay, I just try to tell you what's going on around the industry in aerospace. So this is the very important one. Google tried to claim the supremacy, but other companies say, no, it's too fast. So it's very interesting story, like, Super Bowl, something like that. So some people speak, some German company, scientists or, Asian company, they were talking about this, a quantum revolution. In the 1927, in the Soviet conference, a bunch of future Nobel Prize winner there in this meeting, there's define the quantum physics, quantum mechanics future. This is a term from Newtonian mechanics to quantum mechanics. And they were terming the first quantum revolution is the atomic bomb, the Manhattan Project. Nuclear physics, benefit a lot from quantum mechanics. Richard Feynman himself worked on the Manhattan Project. And the second quantum revolution is the Bardeen, Shockley, and the Breton for the PN junction, bipolar junction transistor, 1948. They also got Nobel Prize. So I can tell each of this step, a lot of people get Nobel Prize because of this, and in the Bell Lab. Then people are talking about, there's a kind of false ambiguous line with the second or third, but some people think we should call this third revolution. For 1998, then Michael Mosca and Jonathan Jones and also later, I think it's Dr. Chong in UC Berkeley, IBM, Almaden. They were said the first, computer with 2 qubits. That's actually the breaking step. Of course, later on you can see Shanadal using the photonic quantum computer, and then you can use D-Wave using annealing. You can see this kind of revolutionize, not only computing or there's also many industry, including aerospace. Then so I think in 2000 something, IBM claimed the first universal quantum computers for business and science. Pay attention to the words universal, because some of the quantum computer has limitation. You can only use in certain cases. You can show the advantage of quantum computers. And IBM claimed this is the first universal, can be used for any problems. So this is a breakthrough, and the people are making games, using this. So a lot of things going on, and this is Microsoft, which is also an important player, but I think they're mostly working on the cloud and algorithm. They are probably not working too much on the hardware. So just to show you what's going on and explain what is quantum, I'll talk about it, what is quanta and what is quantum, what's important. And you already saw a little bit what is qubit. Qubit is using quantum mechanics equivalent to the classical bit 0, 1, but because superposition, you can carry multiple states at the same time. And what is quantum computing is to harness the quantum physics, superposition, entanglement, interference. There are a couple of key persons in the series, not theory, and the proposal you will see later on. So there's another important aerospace company. You will be very surprised how many aerospace companies actually moving forward. Honeywell and their specific division, and they feel there's great potential quantum computer on aerospace and defense, telecommunication, manufacturing, data source, big data, oil and gas, pharmaceutical, chemical, and the financial institute. The Microsoft, of course, they kind of define what they were trying to do. One important thing is cryptography and simulation of nature using quantum mechanics. Another very important thing that you can do is optimization. Companies, they are doing like airline scheduling, things involving optimization. Quantum computer will do a very good job. Another thing is the buzzword, machine learning, which we can talk about it in the future. We are trying to develop the program as well. Quantum machine learning, deep learning, and also like Google search. These the kind of things that you benefit a lot from quantum computers. But you cannot do everything. Using supercomputer, there's some kind of limitation. Sometimes it just doesn't show the supremacy. It doesn't help using quantum computers. Oh yeah, okay. So this is a company which is very important because they claim the first commercial quantum computer is D-Wave. They have been doing 250 application from chemistry simulation, healthcare, logistics, automotive design, airline scheduling, material science, machine learning. You're going to see, it is a very important player. So I can see this. This is important vendors these days. They are selling quantum computers, the D-Waves, but it's a different scheme, and it's very expensive. So that's why I'm saying the next 10 or 20 years, generally is considered a very important step for quantum computers. The company who actually build the quantum computer that who use quantum computing are Microsoft, IBM, Google, Honeywell. There are actually a couple more you will see. They're developing. That means they don't. For example, Lockheed Martin, they bought the quantum computer from D-Wave, but they don't build the quantum themselves. But they use it a lot. You can see the Intel. So Lockheed certainly has something in their mind. So the next few slides, you just show you list of companies you see that a lot. They are involving in quantum computers or using for quantum communication. Airbus, the highlight, aerospace company. The next one, Booz Allen Hamilton. Sorry, kind of shifted a little bit. It's another important player in defense industry. Then the next of it, you can see D-Wave, which is very important. And you can see Honeywell. There are a lot of other companies like Fujitsu. They're very big in quantum computers. But I'm just trying to highlight why aerospace need to pay attention to this and what the aerospace company has been doing these days. HRL Laboratories, which is not Malibu, is very important, as well. And you can see Lockheed Martin, is a very big player. Maybe there's some, maybe I ignored it. Northrop Grumman, I forgot to highlight. Northrop Grumman, also move on to it. And wow, so it's a little bit. But racing, we can also, I'm going also do something, but it's probably people don't know what they are, what's the status right now. Okay, so this is just a list, try to show you that there's a couple of things that establish the basis of quantum mechanics. For example, the double slit experiment. This will help you to understand why we need to work on it and why quantum computer is important and why this solve the limitation of current is microelectronics. There's a link to Richard Feynman's explanation on this, but I think we have a couple of slides on this, so we're not playing it. And tunneling is another important feature that has been, everywhere, like scanning tunneling microscope. These can only be, explained by quantum mechanics. It will play a very important role in quantum computers. So the quanta, the words come actually from Einstein. And actually, contrary to what people are thinking, he's great, well known for general relativity, special relativity, but he didn't get Nobel Prize from the theory of relativity. He just got Nobel Prize from the photoelectric effect in 1905. Then he felt that those photoelectric effect can best explain if the photon is actually a particle. And it is actually, Santosh.
Oh, go ahead, finish. I was going to mention something once you're done with it.
Oh, you want to say something?
Not yet. I just raised my hand, but just go ahead, finish. I'll mention something after you're done with it.
Just let me know. I'll keep in mind to move the mouse away. So at this point, it's very important because in the old time, it's either Newtonian mechanics, things move like a particle, or like a Maxwell, Faraday, that's things like electromagnetic waves. But at the turn of this 20th century or the end of 19th, people started to feel something wrong. A lot of things cannot be explained by either one. So this is one classical example. If you shine light, on like a zinc plate, and you apply the voltage electrode, and then you change the frequency of the light, and then you realize there's a cut-off, frequency, and people could not explain. And the theorists try to come up with very amazing theory, just cannot. Einstein finally said there is a barrier you need to overcome. You have to pop up give the energy so the electron from the material, surface of material, can be energized and be free from the bound state of the atom. So the cut-off energy, and he kind of termed it, this is a quanta. So light is actually a quanta, it's a particle. And it is unthinkable. That's how I got Nobel Prize. It's not relativity. He will never realize that. He should have got several, but no, he got one Nobel Prize from photoelectric effect, and I think around 1920 something. And around that time, young people, de Broglie, he's from aristocrat in France. Then he kind of proposed that a particle can have a wavelength, which is described as de Broglie wavelength. You see, is the Planck constant divided by the momentum of the particle of the wave or photon. They both got Nobel Prize because of this. And another Nobel Prize is Mr. Arthur Compton. And he somehow did some experiment, and he feel that, wait a second, he used X-ray, and he put on some crystal, and he moved the angle of the detector, and moved, and he found something very bizarre. He felt if you see that on the left, the lambda, the X-ray coming in, and he with the surface, the atom. And then in the classical theory, the scattered light should have the same frequency, but it's not. This puzzled so many scientists at that time. How come? It should not be. So if I realize, if you treat X-ray photon as a particle, and it's like a collision, and because the recoil energy, it lose something. So that's how the frequency change. So people come a big shock. If they start to change and think, okay, those waves, can also be particle, then they can explain a lot of questions that they got several Nobel Prize. This. So this which include the Newton law, or the motion, and to the quantum mechanics, harmonic oscillator, things move around. So on the right-hand side, you can see this is a very simple equation in physics, to showing how classical mechanics defined it. And you can see the energy level is actually continuous. So you can see the picture here, the red dot. Actually, this is animation, but it's not. I'm not trying to do it here. It moves left and right continuously. But on the left, if you treat it as quantum mechanically using Schrodinger equation, and you can see the energy actually has a level, depends on integer n. So it become quantized. So this is actually the breaking point for the quantum physics, quantum mechanics, experimentally and theoretically. So there is a very important thing is called the particle wave duality. Then this is actually experiment I was about to show it. Feynman was trying to show if you shine electron gun on a double slit and put a detector, and you can see kind of distribution of the particle, wave-like particle. This is unthinkable by classical thing, and I'm going to show this video. It's fun. Okay, let me see. It's all right. I'll praise it in a separate different way. Let me see here. Where was it? Okay, here.
Ken, the Einstein having discovered the quantization of light, is that what led to the development of the laser?
Yes, around that time, yes, because laser depend on is the lamp amplification. Oh, sorry, let me show this first. So this is particle view of this. So you should see this kind of particle behavior passing through the double slit. But if you consider the wave, the classical wave, then you will see the familiar diffraction pattern. And with quantum mechanics, quantum object, so it's still particle, but the distribution is a probability, no black wave. But if you put the measurement there, you destroy this kind of duality, so you will behave not like a quantum object. Yeah, so this is I found this a good kind of animation for the issue here, because quantum mechanics, things, especially at a certain scale, doesn't behave like particle or wave. It's both. So this puzzles a lot of people, but unfortunately, due to this, a lot of experimental work in the 20th century, early 20th century, that's the best way, to explain all things. And that's how the atomic bomb was made. Without quantum mechanics, it was simply not possible. Of course, Einstein was not happy, but that's the way it was. So Santoshi, if you want to say anything, please just go ahead.
No, that's all I wanted to say was about the laser, because that's what led to the development of the laser.
Yeah, the development of the laser is a little bit, because yes, the concept was there. The Ruby laser was there, but the technology was not mature enough. So I think it's only after World War II, they were able to material-wise, they have to achieve it's called the population inversion, which is not easily done, before World War II. So you have to achieve population inversion in order to have the amplification by light, light by amplification of, of the photon. So laser is actually abbreviation of L is light, A is amplification, S is stimulated, E is, I think, is energy, R is a kind of redistribution, this kind of thing. I forgot the R, but that's basically that it is. Inversion and then redistribute it and then release the.
I believe it's reflection, because you have a mirror on one end and the other end.
Yeah, that's the early stage. Yeah, so basically laser is actually abbreviation. It's a jargon. But the concept was there, but the technology was not mature enough until post World War II. So okay. So if you apply mechanics, this is also something kind of puzzle people. If you to explain that for a single atom, one electron system, for hydrogen atom, then you can solve this, analytically or by computer, and you found this, energy is quantized, this kind of match, and the energy level transition is also quantized, and you have kind of selection rule. But this surprised many people. If we're classical, if the electron move around just like moon move around the Earth move around the sun, you can have any continuous energy level. And this is another view, in those atoms or electron, they have intrinsic spin, and they also have intrinsic spin, but they also move around the atom, and then you have the spin angular momentum, you have the orbital angular momentum, and they interact with each other. For low atomic number, this is called LS coupling dominate, and for large, then you have the individual coupling for JJ coupling, and the energy level quantize. And the reason why I mentioned this one is Stern-Galak, because it's another classical experiment as showing that once you put a magnetic field for those electron or something, and you come out with either spin up or spin down, it's called a measurement. So this is related to the quantum computer later on. If you do the measurement and you collapse the superposition, and you have measured state either 1 or 0, spin up or down. And you will shift to a jargon called eigenstate. It is this is one eigenstate, another eigenstate, but it's not a superposition state. Okay, so another issue about quantum versus classical is, classical computer is always good, like GUI, GUI, hardware. It doesn't need quantum computer. So you'll see a picture later on by D-Wave that actually quantum computer is pictured more as a co-process, like 287, 87 in the old days. So a lot of things like this, and the quantum computer is not intended to be the supercomputer. It's only applied for certain problems that's most suitable for quantum computers. Then I will explain, the 2 to the end state due to superposition. Then you can achieve exponential advantage for the flaps, operation, floating point operation. So some people calculated estimate for different kind of quantum computer technology, qubit technology, how many qubits need to kind of show that you can be the supercomputer. But this thing keeps changing, as I said, because algorithm used, and also the issue involved the stability of those systems, which we will see later on. So this just try to draw some analogy between classical computer and the quantum computer. So this is kind of analogy for on the right is the classical computer. You have the gates, basically 0, 1, 0, 1, but you have the AND gate, OR gate. You can do the plus, minus, multiplication. That's the basics of the computer technology these days. So say you have chip, you have the gates inside. So similarly for quantum computer, you have the same thing, but it's slightly different. You also have the classical input. But then you have, there is called a quantum gate. Similar like AND gate, OR gate, they have, called Hadamard gate, poly-S gate, all kind of different CNOT gate, control gate. Similar analogy, but the fundamental thing are a little bit different. But once you establish the truth table of those gates, then you can do basically everything and more than the classical computer. Okay, so right now these days, I'm going to talk about why the quantum computer become more and more important, because as I said, the Bardeen, Shockley, Breton, they got the Nobel Prize for the bipolar junction. Based on the theory, the physics phenomenon PN junction, this is already quantum mechanical. But if you use classical because diffusion between the junction N-doped and the P-doped semiconductor, then you achieve different potential. Then that's then you apply external voltage. That's what Santoshi was talking about. Apply voltage to the chips, then you have achieved the 0 and 1 and the gate operation. But they are reaching some limit right now. This, for example, there's a TTL 5 volts standard bipolar transistor junction circuit diagram and the actual device profile. We have semiconductor, P-dop, N-dop, collector, emitter, and base. And I think in the most 20, 30 years has been shifted to CMOS technology. It's lower voltage, lower power consumption, so you can see again the device profile. This is a dominating technology these days, and it's actually based on the field effect transistor. It's kind of modified. You have the metal gate and put a gate oxide over there, and change the voltage, and you change the distribution of the PN dope layers, and you achieve the potential between layers. That's how you amplify things. So you can see this is a family, a transistor, junction, field effect. They have MOSFET and depreciation enhanced. There are all kinds of variation. This is the fundamental thing of these devices. and of course, you are using the USB flash drive or the memory card, like Raspberry Pi or your camera, is based on also semiconductor CMOS technology called NAND, flash memory. So basically, by manipulating again the dope iron level, chemical distribution, tunneling, and you're able to keep the kind of electrons in certain area. Then with the change of word line, and you can keep the electron in certain area for a certain time. And you change it, you can erase it, and you program it like an apron. So these are the basis for our technology these days. But and the people have enjoyed that. It's called the Moore's law, which is very important for a quantum computer. Dr. Gordon Moore is actually Caltech. So Feynman was Caltech. Gordon Moore is Caltech. If you go to Caltech, you will see a statue of him there, and he's now 92 years old. He's the founder, I think, is Intel. So the famous Moore's law predict or says that every 2 years, there's the density double. The microchip, on a certain area, it increases. So Santoshi, again, if you want to say something, just speak up.
Just a little interesting tidbit here. There is a connection to aerospace when it relates to Intel and Gordon Moore and
Fairchild,
Andy Grove, and all these guys. They all started out at a company called Fairchild Semiconductor,
yes, Fairchild,
where they invented the world's first integrated circuit. And Fairchild Semiconductor was the electronics division of Fairchild Aircraft, which makes the A-10 and of course Fairchild Republic. That was what's the A-10, and the Republic made the P-47 Thunderbolt in World War II. And of course, as a cousin, interestingly enough, the AR-15 rifle was made by the Armalite division, the armament division of Fairchild as well. So they're all related to each other in an interesting way.
Yeah, and if we go to Irvine, the Fairchild actually still have an office there, at least a few years ago when I stopped by in Irvine near UCI. You can go there. It's very interesting. Still there. Okay, so Moore's law is like a God law, these days, for somebody. People have been making money after this, keep growing, kind of breaking everybody's, people say, oh, maybe they'll reach kind of plateau or something. No, it keep growing. And I want to show a lot of companies like Samsung or like a Taiwan semiconductor company. They are, technology going down to even 2 nanometer these days. The angstrom is atomic size. Atomic diameter is around angstrom. And the nanometer means like 50 size of atomic size. So that's just amazing. So this is a news, because make great America great again. So Taiwan Semiconductor Company is going to open 5 nanometer factory in Arizona. So you can see this kind of nanotechnology chip company moving very fast and still following the Moore's law. But it comes with, you think it's approaching the atomic scale, and people start to see a lot of concern. What's going to happen if we make it smaller? Is going to work or not? And you can see that these days the chip generate a lot of heat. There's another issue with the density of the BJT or CMOS in per square area. It's getting hotter and hotter. And also when you get there, then the quantum effect, the tunneling keeps to show up. It's not going to be easy. It's going to be very tough. So the electronic industry has been trying to find the next paradigm and the ship over there. And the quantum computer is what they were thinking about. So this come down to this bit and qubit. So we went through this quantum mechanic history is to just show you is kind of first is quantized. So energy level is quantized. So then it's described by the state and not by this classical gate. So you can have the superposition. You can point it anywhere in the sphere and in the qubit. So that's why they get the advantage of this. So next I'm going to tell you the important person. We already, this Feynman, you already saw that, Einstein, but there's a couple of people, that actually paved the foundation of our quantum computer these days, which are very important. These are in text, but I have a few pictures for those people. So I don't have a picture for Yuri Manning, but it's in Russia, so we don't elaborate a little bit. We can talk about him a little bit more later. So basically, I'm going to show a couple pictures here. So basically, Alan Turing is a very well-known British mathematician, and he, there's a Turing machine, and there's American mathematician, Church. So there's called a Church-Turing kind of thesis. Is basically it's complicated, but you can basically say that for each, kind of a problem, there's a corresponding Turing machine that can have the algorithm to solve it. So basically, that kind of pay the foundation that any of the problem you can kind of have a machine, a computer, or kind of algorithm, quantum computer or anything to solve the issue. So now it come more closer than, of course, you already saw Feynman, 1959 and 1982, very end of Yuri Manning was around 91, 1982, similar role as Richard Feynman in Russia. And Russia also have their own quantum computer as well these days. So two important persons, one is Peter Shor, you will hear a lot, and there's David Deutsch. There's another person, it's India scientist is called Grover. It's important for breaking the code, for hacking things, those kind of things. But Peter Shor is a scientist at MIT, and this algorithm basically is a quantum algorithm for factoring exponentially faster than the best current node algorithm running on classic computer. But because of this, people got very scared, because if you can break the prime number or number so fast using the qubits, and they can break any code very fast. So got people hype about this quantum hacking, quantum things. But you will see later how the RSA respond to this. And David Deutsch basically was paved the foundation for the quantum Turing machine, the architecture for it. He also tried to attempt to kind of prove it in a certain way, but he didn't make a computer out of it. It is a kind of theory and prove that it should work and pave the architecture. These are two key persons in the modern day, and they happened in the 80s and the 90s, very recent. And another two person is Paul Benioff, that's from Argonne, a physicist, and he, basically demonstrate using quantum mechanics model, computer, pave the way for the first quantum computer is using Schrödinger the equation and the Turing machine. That's from Paul. But who make it more, the first. Well, there are a lot of people making quantum computers, but really the first demonstrate with the 2 qubit using, kind of any physical system was these two scientists, a physics professor and, Dr. Jones and then Dr. Mikhail Mosca. So they built the first one, then quickly IBM Almaden by Dr. Isaac Chun and Mark Kubinek, UC Berkeley, and with MIT and Stanford, they built the same system, 2 qubit NMR quantum computer to solve the David Deutsch, the proposed issue to prove the quantum computer can work. So this is actually the fundamental thing, and there's a big name in this industry. Another big person, but it's not really big, but it's because this very, very genius Indian American scientist, Kumar Grover. He kind of invented a Grover database search algorithm. So it's hailed as as the kind of god, for this kind of internet search and also code breaking. So these are by words. If you want more detail, then of course you have the key person. You also have to see the key opponent, what they are, competing against. Definitely not our laptop. They're competing actually the fastest supercomputer in the world. Right now, according to news, the number one seems to be Japan, but we always talking about the IBM summit on the lab, and they keep breaking their own record. But the Fugaku, the Japanese Fugaku, seems to been doing very well, and maybe hard to compute the number, but they're both fastest computer they achieve. The numbers keep, they have 10 to 20 as 18 zeros, trillion, quintillion, those numbers keep growing, it's never just giga. So these are the opponent they are compared against. Okay, so this is the quantum superposition. So you see the diagram for the sphere. It's called a Bragg sphere, but put it in mathematically, or kind of way to write it down is that if you have a system, spin up means 0, spin down means 1, then you have the coefficient to describe the superposition of these two states in the qubit. But overall, the square of the coefficient is the probability of the qubit is in certain spin up or spin down state. Remember the double slit picture, it could appear in this and that area, they form probability distribution. But overall, the probability conserved as it has to be 1. So another important concept is in quantum entanglement. I'll talk about how the physically achieve people talk about this a lot, but it's actually theoretically, yes. Like Stuart was talking about long distance, it could still have connected state that puzzle people. How come we can transmit so fast? But in reality, it's not that easy to create the entangled state. So basic entanglement is the ability quantum particle to relay their measurement result with each other. It's actually, if you look into it, it's actually not too complicated, but because the way the news media spreading it make it very confusing. But this is an important feature because this is how the exponential you saw. If each of the qubit can be entangled together, so you can have exponential power for the parallelism, simultaneous, computing power. But you will see, practically it's not easy to make. So for example, this is a well-known Bell state, is one kind of most stable entangled state. So it's composed both 0 and 1, but because a certain way you physically made it and you put the circuit for it, it's become very stable. So what happened is if you realize in one qubit and this is in a 0 state and the other one has to be in a 0 state if you are entangled. But it is very nice and people got scared, what is that? But the problem is if you look into it, I asked several experts in this, the problem is that our technology these days, I don't know about universe, and maybe universe something already created there, but if we for man-made entangled state by many different ways, it's very difficult and the lifetime is very short. So honestly speaking, it doesn't exist the problem that you transmit the, simultaneously, those breaking the law of, fastest speed of light. Basically, for example, this is one of is a nonlinear optics. You send a laser pretty something called nonlinear crystal. You create a downstream. It's called a parametric down conversion. Then you create the entangled photon. That's what the Chinese is doing. But these are not photon, as you know, there's no mass. What it was entangled was the state, the quantum state of this photon. It's not actually even transmit anything, it's the state of the quantum state of each of the items. And they are not very long life. So there are a lot of issues. Practically, the concern is not there, but on the news, they already don't tell you those things. So method of creating entanglement, one is change of polarization using nonlinear optics, laser, nonlinear crystal. But you can also use it like, this, like superconductor, quantum dot. That's what the Japanese has been using, quantum dot. But again, these are very long-lived. It's very difficult to make. But if they can make it, it's proven. So that's the hurdle that quantum computer has to get through. Okay, so this is just a little bit more. Again, all those things come from public domain. Sometimes I borrow from Wikipedia picture just for faster, picture. So this is the nonlinear optic, way, of doing things. So it's not violating any physics principle. It's just the way it is, and it's not try to beam up, a person, like Star Trek, or try to move the mass or energy faster than light. No, that's not it. It's basically just to have the state, one photon and the other photon, they are linked. The information are linked. That's all it is. And another important issue, when you see the animation, if you start to measure it, put the eye next to the slit, it kind of collapses the superposition. So any noise or measurement, you will collapse the quantum state. You will become either 0 or 1. Remember the Stern-Grach picture I showed, put a magnetic field. up and down, you will only see 0 and 1 after the measurement or after interference. And noise is a very big issue these days. Microsoft try to do a lot of things, topographic thing, wrap things around the chemical they use it for the qubit. There are several important jargon or important application. You will hear a lot of things. One is the super dense coding, in which you, instead of using, say, for example, instead of using 2 classical bits to transmit information, you can use, say, 1 qubit, or more exaggerate, as the number goes down, you can use fewer qubits to achieve the same thing. You need so many classical bits to do it. But in doing that, you need to have create entangled, called a Bell pair, which is entangled state, and they pass through certain kind of gate, Hadamard gate, CNOT gate, and then you have to reverse the measure and send a classical bit. That's how we do it. If you can do all this, then you can achieve, super dense coding, which means, but literally, you can send a lot of information by using very few qubits. So that's all it is. Nothing very complicated. Another issue is quantum teleportation. Again, this is not trying to teleport mass or energy. And also there's an issue, people think, okay, in quantum computer, you might have heard that some people say you cannot clone a qubit. You cannot delete a qubit. I think that they have something to bypass it. They do sometimes entanglement and indirect way of kind of reproduce a state of a qubit. Of course, they cannot copy the exact photon or electron, but they can kind of create the same state on another electron. That's why they are trying to do. So the teleportation is similar thing. So just some, you have some information you want to pass through, and you have basically this is to send a qubits, not for person. And this quantum teleportation honestly is not simultaneous. It's not instantaneous. And again, you have to first create, entangled state. You see this, thing, and when you see this meter-like thing, it's called a measurement. And then the process is input the information, then entangle the state, then you measure it, then you send the classical transmission to the receiver, and then the receiver already have the splitted entangled state, and they will double check, what is your measurement, and they compare theirs, and this way, then they have the information already in their hand, but they kind of decrypt it, so that kind of it's kind of reproduce a state, of say an atom or photon that's split from the initial entangled state, then to achieve the same state as the sender. That's all it is. Then you actually require the classical transmission, and it's not instantaneous. So it's absolutely not what the media was saying. The Chinese can beam you up. That's definitely not. Never. Okay. So then another important thing other than super dense coding, teleportation, another thing you saw it before, right? The Aerospace Corporation put on their website, the quantum key distribution is for the quantum cryptography. So because you can carry a lot of information in a qubit, so people are afraid, and the financial and stock market, those things, aerospace defense contractor, their code will be broken once the supercomputer get to in fact pretty soon. But you can see the response. You can look at the website itself, the RSA, NSA, National Security Agency. They actually analyze this, and they come to the conclusion they are not going to support the quantum key distribution. They post their reasons. They say this is only a partial solution. It's need a special purpose equipment, which is true. In infrastructure costs, and actually by this you increase inside threat risk, and you have to securing those quantum keys is actually a significant challenge. It's a big hurdle. It's not completely mature yet. Then you have this, and you kind of cause the risk of denial survey. You will see actually these days the SSL, you see the internet protocol, they start to explore this quantum secure layer. But anyway, the conclusion then says, no, we don't support this. Instead, they come up with something called the post quantum cryptography, or called the quantum resistance. They have some kind of algorithm You know, if people use Shor's algorithm or Gross algorithm to attack to break the code, the NSA actually proposed a post-quantum resistant algorithm. You know, so you can see here, this is what the RSA view. They work with the National Institute Standard. The picture that the PKI algorithm code will be broken by quantum computer in 2026, 31, assuming the universal computer will be available. And so then you have to worry about this. Then you have the different kind of email security, website security level. The NIST, what I heard was that they are putting some kind of, you cannot say contest, but a kind of proposal by the end of this year or early next year. It's a post-quantum resistant cryptography, which is supposed to prevent or delay the quantum attack, you know, breaking the code. So what RSA and the National Institute Standard will tell you is safe. Don't worry about it. It's not right now, and even later with the post-quantum resistance, they don't need the quantum key distribution. But you can see a lot of aerospace companies still very interested in this for special application. So now we are talking about, some experts say maybe not to say too much about quantum supremacy, but this is also the way for us, to understand what the issues are and what are the existing system. So as you see from the Moore's law, more compact of the electronics, integrated circuits, then you have a lot of material issue, tunneling, spin orbital interaction, and then you have to optimize the circuit, and there's that issue of entropy, heat generating issue. It's very difficult to overcome. But if you can achieve the qubits, fewer qubits, and they actually by nature they don't do the same way as the existing microelectronics. They don't generate so much heat. So basically, but it depends on the suitable system. It's not for all the system unless it's a universal quantum computer. So that's what I'm trying to do. So the next few slides is a few companies that have their doing quantum supremacy. They claim, for example, we talked about the 2000 Sycamore, the Google 19, 54, 53 qubit using nonlinear superconducting resonance. This also comes down how do you achieve basically the supercomputer. Then you can see the IBM, they were doing superconducting, and the China, this is Canada company, Shenandoah, is doing photonics. Then there's IBM, mostly supercomputing. I think they have more qubits, but this is just the history of what they were doing. Then you can see IBM again. I think that's just early. This is a attempt for the companies to achieve the quantum supremacy. But these days they kind of toned down a little bit because somebody changed algorithm on supercomputer, they can do much better. So their claim may not be true. For example, Google was seriously challenged, for their claim for supremacy. So the D-Wave, you will see it play a very important role. They work with USC and Lockheed Martin. And the Google verified DF actually is making the real quantum computers. They are using superconducting things, and they're using a method very different from others. If you look at the website, they can achieve like 2,000, 5,000 qubits, but it's a little bit different from, but this system can only be used for specific problems. It's not universal, not what IBM has been trying to do. So that's why they use a phenomenon called the quantum tunneling and Ising model. So they apply a field, and so for classical simulation or optimization process, you're trying to find a solution for a local minimum and global minimum. But for classical ways, you have to spend a lot of time, classical computers time, and you cannot pass through this barrier. You have to try to do a lot of simulation, increase the sampling. But this is a well-established method using Ising model and the quantum tunneling. They in a simulation apply a small field and allow you to tunnel through, and you can see it's much faster to reach the minimum. So this is how they achieve. By doing this, they claim they can do much faster to find the global and global minimum. But the problem has to be very specific, especially about optimization. And there's some, assumptions say, variables are discrete. It cannot be continuous. The optimization is quadratic. the object function is quadratic, and or constraint can be efficiently represented by a quadratic objective. This is all the deep detail. So they're doing a lot of business. They sold the first commercial quantum computer, but they are very limited. But they are trying to, increase the qubits. The latest I heard is 5,000, to overcome those things. Yeah, 5,000. So obviously they have been doing great jobs. But again, D-Wave is for specific problems, not for all the universal cases. And they utilize a situation called the quantum annealing, which kind of brief idea, actually. And those many companies also focus on, SDK, software development. For example, D-Wave has a very famous Ocean software. And this is what I'm saying. At the bottom, you can see CPU and the GPUs. But now there's a term called the QPUs, the quantum process unit. So that's what I said. They were picturing using quantum computer as a coprocessor, like all this math processor or the graphical processor, but not intended to replace the classical computer. And there's no such intention. It has to work together. Okay, so as I said, some company trying to develop software to work with their quantum computer, and some company they don't have their own quantum computer or spend money on it, but they're developing algorithm. Microsoft, we can see D-Wave, Ocean, IBM, 1 qubit, just lots of this, a lot of software, different things. And as I said, there's a lot of challenges because the next 10, 20 years, they kind of start to see the verge of claiming the quantum supremacies, but the supercomputer is also developing very fast. The change of algorithm, computer science also change a lot of claims. So people really say you probably need to go up to a couple hundred, 1,000 or even tens of thousands, especially if you want to simulate, like you see earlier, the chemical. And if you want to simulate each of the electron atoms, then you need to have, almost equivalent number of the qubits in order to be able to simulate the nature. So another issue is most of those qubits need low temperature, and because of those issues, only those big companies can afford doing that. And mostly they provide this for cloud computing, and you can start to use it for like 5 qubits or a few qubits on the cloud, but you are going to compete with many other users, but it's very limited. Then it says the code these days also called edge computing, so there may be some kind of local possibilities. So here are a couple physical process you can do: ion trap, Joseph junction, superconductor, quantum dot, or diamond defect, or quantum annealing. But quantum annealing is not for universal quantum computer. And so this is the copying process. Currently is not exactly the same, but there are a lot of great potential. So just quickly summarize that there are a lot of advantage. There are a lot of computation, like you heard, that especially optimization. Optimization applied to machine learning, artificial intelligence. Anything related to this nature, it will be good, to use quantum computer. And also the things for simulating natures, like chemicals, medicine, or search, like you heard, the Grover search algorithm, and cryptography, the quantum key distribution, even though RSA denied, but there's also some kind of advantage. And the radar, high speed, people are doing radar using quantum computation. I already mentioned because artificial intelligence and machine learning basically is kind of optimization process. We do it by hand. They just do it faster. So it is some disadvantage, as I mentioned, it heavily depends on algorithm. So quantum computer depends on good algorithm to use it, and they need low temperature. Some is almost as minus 460 degree Fahrenheit, or or minus 273. That means 0.015 or 13 Kelvin degree. And it's not really open to a public. Yeah, they have some cloud thing you can use, but it's just for trial. And they are selling a system, but it's ultra expensive. So, but next 10, 20 years is key. And the internet security, so there's certainly, it's a very important issue. But you hear what RSA is trying to do. Okay, this is a quick summary. So it's important. It's on the market. Aerospace company has been doing it without much people paying attention. Raytheon, Northrop Grumman, Lockheed Martin, Honeywell, HR Laboratories, and Booz Allen Hamilton. I'm pretty sure Boeing same too. It's not intended to replace classical computer. It's an advantage, but high cost for now. So for us, we have been trying to develop, the related program because it's relevant to aerospace and STEM. So we are trying to develop materials, demo, and you will come up as it goes. So this just, some kind of additional thing, basically, the discussion is here up to this point, but this is, I mentioned the first 1998, the first quantum computer was built using the nuclear magnetic resonance system. This is an example of why quantum mechanics come in, because if you apply the field, if you don't apply the field, it's a superposition of different state. But if you apply the field, the energy split, energy quantized. So that's then you can, by manipulating the chemicals or the atoms, and then you can achieve the qubit. But you can see it's very high maintenance. Look at those cryogenic. Thing is every day you consume a lot of things, and equipment, environment. So yeah, so that's what I have. I have a couple of slides, but that's just for if we need it. So that's what it is. So this is now it's open to the floor. So if any question, discussion, this is intended to kick off the AIAA Los Angeles Las Vegas section, quantum computing, quantum communication program and events and discussion, and further maybe like outreach or education stuff. So we are doing it, just let people know that's the main message for this. So Santosh, please go ahead.
I want to apologize. I misspoke earlier. The R, you were correct. And laser is actually for radiation, not reflection.
Yeah, radiation. You're right.
The reflection is involved internally with the ruby laser, but the R stands for radiation.
Yes. The most important thing is light generated by the inversion of the population and then emit the radiation. That is the laser light. Yeah, they consider light is, you see, that's a very interesting. Light was considered electromagnetic radiation, just like it's like electromagnetic wave. It's just different frequency. But now you can view those things also as particle. So that's how the quantum computing try to take advantage of. So I see a couple, radiation, yes. Oh, mouse, sorry. So, it's the quantum computer is actually kind of very interesting, but, there are various technologies that has, been explored. So far, the Chinese is ahead. They are using the photonics, nonlinear optics to achieve this entangled state, and they do it with satellite, with different locations, Austria, different places. They kind of prove that it can the entangled state could be very apart, but nothing to be scared because you knew there's there, and those very difficult to create, and it's not very long life. So there's no practical application as for now, and there's definitely not the beam me up Scotty like a Star Trek is nowhere. It's not like that, and it's basically to kind of reproduce a state to remote entangled photon. It's kind of doing that kind of thing. So it's not actually sending kind of energy over there, but it's kind of, because doing this way, you can kind of put the information over, but it's kind of recreate the state over there. But you have to create the entangled state in the very beginning, and you split the Bell pair, and then they split. So it's definitely not from nowhere. But in space, that might be different. The universe creation that might have some existing entangled something over there, graviton or something like that. But on Earth, for man-made, it's not the case. So there's nothing to be scared. But there's a competition, using different technology, who might actually win the supremacy and get the market. But from this kind of trend, you see, even Amazon is trying to put some effort. So it looks like even if somebody achieve quantum supremacy, it will be heavily challenged and the other company will follow, and it's probably not one will take all the market, but different technology will be much cheaper and much stable. And a lot of effort has been put into is the noise issue. So it's fun, but I think it's very good, like education process, and it's also very good to try to see how it goes and catch a trend, and maybe there's some opportunity in different companies, including aerospace, but the other thing is still in development. But it's good to catch up. Maybe it will come it's a mainstream pretty soon. Yeah. So okay, I see Mark raise hand. So Mark, go ahead.
Yeah. If this is all theoretical. If a visitor from another galaxy came to Earth and entangled our space with entangled it, then they went back to their galaxy, could they be in communication from their galaxy to our Earth? Is that possible?
Okay. Yeah, as I said, if it's something in the universe, that's a creation universe, that's already there, like creation, like 3K background radiation, those kind of things. If it's Big Bang, it's already there, then this is possible, But if you're saying like if somehow the alien has the technology to create, the long-lived entangled state when they travel before they set up their journey and are passing light years, thousand, 10,000, million light year and come to Earth. First of all, the entangled state they created might have vanished. So that's what I'm trying to say. So then you assume they have such technology can, like a God, they can have this forever entangled state. Theoretically, they have to send some kind of communication to the alien here on Earth, tell them what they did, they have to perform some kind of measurement on their end, then tell this alien that they did something, and then they compare, then you can achieve the teleportation. So yes, it's possible, but it's not right away. Yeah, it's possible, but you still need some kind of way to tell the alien here that something happened. They did measurement, please compare, and if it's the same, then yes, then you achieve the teleportation. So you see what I'm trying to say? But if it's universe, it's been created by Big Bang or God, there's already forever there, is entropy-wise, it's stable. Yes, it's very likely, but if it has first condition, it has to be long-lived. Secondly, you have to a second way of communication to tell what and the mother star, mother planet they did, and to tell this alien here, yes, you can do it, but it will come at a very high price for doing that.
Thank you very much.
Yeah, no problem, no problem. It's basically creating a state that initially entangled. Then you kind of relay that information to the other pair that is long distance. But technically, there are a lot of hurdles. But theoretically, it's possible if it's entropy, everything works out, like a universe that might happen. But if for intelligence beings that has to have very advanced. So far, we are very limited to create the entangled state for even a couple milliseconds, or it's already extremely very difficult.
So what I understand is you're saying communication is possible if you have the technology.
To be sure, yes, you have two key technology. One is you have to create a long-lived entangled state. You have to have this technology to begin with. Because all the teleportation, those things began with entangled state. They split the entangled pair, and one carry long distance, and one, that's how you achieve the teleportation. The second hurdle is that you have to communicate somehow, and that is not going to be faster than speed of light. So that civilization has to have another high tech in order to relay that kind of information. So in that, and then you can, it can be achieved, but it needs to be much higher civilization or technology than we currently are.
Right. Thank you for pointing that out.
Don't worry, nothing. It's not going. China is going to send, beam me out Skyward anytime soon. Yeah. Okay. So any further question or anything you want to discuss or anything you heard? it's kind of fun topic. Yeah, there are a couple of things I didn't put there because I realized, time is short. I just want to summarize quickly what's going on, what's in the market, and the main purpose, I said, is important for AIAA Los Angeles Las Vegas section to have this event. We have been trying to do it for 3 or 4 years, but unfortunately, the speaker just cannot commit, in time. And we might have some, somebody soon, but I think it's good time, to let everybody know that it's going on, and we are ready. We are prepared to have a further program, either education or outreach, or this further professional discussion on this, any new development. For example, if Lockheed Martin come with something on the news, that would be worth a very fun event or discussion about it. Or Aerospace Corporation, some kind of satellite communication breakthrough, or cybersecurity. There's a battle between RSA and the quantum scientists. It's kind of interesting. When I saw the news, I couldn't believe it because RSA kind of refused. They don't care. They don't want this quantum. They come up with this counter measure. They have this quantum resistant post quantum. Some people said it's going to be more the mainstream instead of quantum computer. The key distribution in terms of this kind of security, internet security, or whatever thing. So yeah, so and that's another thing. And just to people know, to rest assured, there's nothing to worry, because the quantum, yes, they can do that, but they need time. And by the time they can break everybody's code, the financial code, and the RSA and the National Institute Standard already have a very good measure to counter it, either the Peter Shor's algorithm or the Kumar-Grove search algorithm. So they just tell you, no worry, they are ready. There's nothing to worry about. Yeah, I've been trying to do this, trying to get speed because, we have members, speakers that come read the news. That's just so scary. But the news exaggerates so much, and that doesn't make any sense. So I think it's better to come down to, and that's also point out the AIAA is, and also Las Vegas section, that's Los Angeles, Las Vegas is very paying attention to this and trying to advance in the related technology, science, understanding, and education. This is very relevant. As you said, Richard Feynman is very related to aerospace, and as Kuma Santoshi mentioned that Fairchild, was founded by Gordon Moore and those founder in the early stage of the Intel, heavily related to A10, and all the other things. So it's highly aerospace. That's very important, and a lot of research institute and company, they actually put space, not only aerospace application as one of the agenda, but they have to find the right algorithm and so to prove that it makes sense to spend the money. But you cannot just use the classical computer, and supercomputer is getting faster and faster. So why can you just use it? Why do you have to do the quantum? You have to come up with a justifiable reason for doing that. But as we point out, a lot of problem simulating natures, especially at the atomic molecular scale, is already reaching the limit of the supercomputer, fastest one. And the quantum is a solution. And when the microelectronic, if they want to keep down the Moore's law, you cannot go to angstrom, atomic. It's just you cannot do that. So there's a lot of heat issue, manufacturing issue. Then the quantum computer is the way out. And they can keep continuing the growth and prosperity, making more money. Enjoy faster computing. If they jump to quantum computer at the right time, they can keep the growth of the Moore's law keep going. But they see a problem right now. It's already 5 nanometer, 2 nanometer, 1 nanometer. You cannot beat the angstrom. Then how are you going to do? It's already a lot of difficulties, material wise, manufacturing wise, those kind of things. Okay, so yeah, so I think there's if you have no question, you're welcome. Just say goodbye and leave or stay in touch. And next week we have the space architecture event. But since you are here, I just want to play this Feynman video. I was usually about to show about quantum mechanics because he explained it very well. this issue is not very long. But if you have to leave, please go, and I'll just enjoy the Saturday. But if you have 2 minutes, it's fun to see how you explain those things about this double slit and the basis of quantum mechanics. I put it somewhere. Oh, here. It's
electrons.
It's a lecture 1964 in Cornell University.
In the beginning of the history of experimental observation or any other kind of observation on scientific things, it's intuition, which is really based on just experience with everyday objects, that suggests reasonable explanations for things. But as we try to widen and make more consistent our description of what we see, as it gets wider and wider and we see a greater range of phenomena, the explanations become what we call laws instead of simple explanations. But the one important odd characteristic is that they often seem to become more and more unreasonable, more and more intuitively far from obvious. To take an example is the relativity theory, in which, for instance, the proposition is that if you think that two things occur at the same time, that's just a subjective opinion. Someone else could conclude that those two events, one was before the other, and that simultaneity is merely a subjective impression. Now, there's no reason why this should be otherwise, really. The things of the direct everyday experience involve large numbers of particles, or involve things moving very slowly, or involve other conditions that are very special and represent, in fact, a very limited experience with nature. It's a small section only that one gets of natural phenomena from a direct experience. It's only through the refined measurements and careful experimentation that we can get a wider vision. And then we see unexpected things. We see things that are far from what we would guess. We see things that are very far from what we could have imagined. And so our imagination is stretched to the utmost, not as in fiction to imagine things which aren't really there, but our imagination is stretched to the utmost just to comprehend those things which are there. And it's this kind of a situation that I want to talk about tonight. Start, for instance, with the history of light. At first, light was seen to behave, it would appear to behave very much like a rain of particles, of corpuscles, like rain. Bullets from a gun, same idea. And then with further research, it was clear that it was not right, but that light actually behaved like waves, like water waves, for instance. And then in the 20th century, on further research, it appeared that light actually behaved in many ways, again, like particles. In the photoelectric effect, you could count these particles, they're called photons now, and so forth. Again, electrons, when they were first discovered, behaved exactly like particles, bullets, very simple. Further research showed, in electron diffraction experiments and so on, that they behave like waves. And as time went on, there was a growing confusion in the question of how the things really behave, the waves or particles or waves, because everything looked like both. Now this growing confusion was resolved in 1925 or 26 with the advent of the correct equations for quantum mechanics. And now we know how the particles, how the electrons and how light behave. But what can I call it? I can say they behave like a particle wave, or they behave in typical quantum mechanical manner. There isn't any word for it. If I say they behave like particles, they give the wrong impression. If I say they behave like waves, they behave in their own inimitable way, which technically could be called the quantum mechanical way. They behave in a way that is like nothing that you have ever seen before. Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different. They do not behave just like particles. They do not behave just like waves. Atoms do not behave like weights hanging on a spring and oscillating, nor do they behave like miniature representations of the solar system with little planets going around in orbits. Nor does it appear to be somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you've seen before. Well, there's one simplification. At least electrons behave exactly the same in this respect as photons. That is, they're both screwy, but in exactly the same way. How they behave, therefore, takes a great deal of imagination to appreciate, because we're going to describe something which is different than anything you know about. This, in that respect at least, makes this perhaps the most difficult lecture of the series, in the sense that it's abstract, in the sense that it is not close to experience. And I cannot avoid that. Were I to give a series of lectures on the character of physical law, and to leave out from this series the description of the actual behavior of particles on a small scale, I would certainly not be doing the job, because this thing is completely characteristic of all of the particles of nature and is a universal character. And it is, if you want to hear about the character of physical law, essential to talk about this particular aspect. So it will be difficult. But the difficulty really is psychological and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which really is a reflection of an uncontrolled, but I say utterly vain, desire to see it in terms of some analogy with something familiar. I will not describe it in terms of an analogy with something familiar. I'll simply describe it. There was a time when the newspapers said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other, but more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate this and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe, and just relax and enjoy it, I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. So that's the way to look at the lectures, not to try to understand. Well, you have to understand in English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you'll get down a drain. You'll get down into a blind alley in which nobody has yet escaped. Nobody knows how it can be like that. So then just let me describe to you the behavior of electrons or of photons in their typical quantum mechanical way. Now, the way I'm going to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast to things that you're familiar with. And so I make it, and by analogy and contrast, first to the behavior of particles, for which I will use bullets, and second to the behavior of waves, for which I will use, say, water waves or sound waves. So we begin first to discuss in a particular, what I'm going to do is I'm going to invent a particular experiment and first tell how it would behave, what the situation would be in that experiment using particles, what you would expect to happen if waves were involved, and then what happens when there are actually electrons or photons in the system. And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. So I start with bullets. Then all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which is just represent the source, which we call the source, and is in fact, in the case of bullets, a machine gun. Then we have a plate in front here with a hole in it for the bullets to come out of, and this plate, in the case of bullets, is armor plate. Then a long distance from here, we have another plate, which I'm drawing only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand that. That's a small point. And it has two holes in it. That's the famous two-hole business. I'm going to talk a lot about these holes, so I'll talk about this hole as number one hole and the other hole as number two. And I'm only drawing it in two dimensions. You can, if you wish to imagine these as round holes in three dimensions, but just say this is a cross-section. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here, which is just a backstop of some sort, on which we can put in various places what I will call a detector. And they will mark that detector, which in the case of the bullets is a box of sand into which the bullets will be caught, and we can count them. That's the detector for bullets. I don't want to have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector or box of sand when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere down here and call that X. And I talk about what happens when we change X. It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions, not just exactly straight on and bounce back. And they can ricochet off the edges of the holes in these armor plates. And finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important. But the most important idealization in which it differs from real bullets is I want these bullets to be absolutely indestructible, so that what we find in the box is not pieces of lead of some bullet that broke in half, but we get the whole bullet, please. So imagine indestructible bullets, or hard bullets and soft armor plate or something. And now the first thing that we will notice about bullets is that the things that arrive come in lumps. When the energy comes, it's all in one bulletful of bang. If you count the bullets, there's 1, 2, 3, 4 bullets. The things come in lumps. They're equal in size, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box. It comes in lumps. More, if I put up two boxes here, I never get two bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between things, you see, slow down the gun so they go off very slowly. Bing, 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 bing. Then put the two things here and look very quickly in the two boxes. You'll never get two bullets at the same time in the two boxes because a bullet is a single, identifiable lump. I call that characteristic of the object that it comes in lumps. So the first thing about bullets is that they come in lumps. And now what I'm going to measure is how many bullets arrive here on the average in a long period of time. So you wait an hour and you count how many bullets are in the can, in the sand, and average that. Now, we call that, if you want, per, let's say we take a definite time like per hour and say the number of bullets that arrive per hour. And sometimes you could call that what's called the probability of arrival, because it just gives the chance that a bullet going through this thing arrives in this particular box, at least it's proportional to the chance. One way to measure is to measure the average number of bullets that arrive over a period of time. Now, the number of bullets that arrive in this box here will vary as I vary x. And I'm going to make a graph here in which I plot horizontally the number of bullets that I get if I hold this thing here for an hour. And I'll get a curve that will probably look more or less like this. Because when the box is behind one of these holes, it gets a lot of bullets. You go, ones that went through this hole, and otherwise it gets them that went through this hole. And if it's a little bit out of line, it doesn't get as many. They have to bounce a little off the edges of the hole. And so it disappears like this. And this is the number that we get in an hour when both holes are open. And I call that, by an abbreviation, N12, which merely means the number which arrive when hole number 1 and hole number 2 are both open. Looks like that, say. Now, I must insist that the number that we're plotting here doesn't come in lumps. You can have any size it wants. For example, there can be 2.5 bullets in an hour. In spite of the fact that the bullets come in lumps, what I mean by 2.5 bullets in an hour is that if you run a long time, like 10 hours, you get 25 bullets. So it's on the average 2.5 bullets. The N can have any size. It doesn't have to be in lumps because it's an average. I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family whatever. The children come in lumps. But nevertheless, when you take the average number per family, it can be any number whatsoever. And so this number N, which is the number that arrive in this container per hour on the average, need not be an integer. It can be a tenth, which would mean under those circumstances that you have to wait on the average 10 hours more or less per bullet. So what we measure then is the probability of arrival, which is a technical measure, the probability of arrival, which is a technical term really for the average number that arrive in a given length of time. And now finally, if we go to analyze this curve N12, we can interpret it very nicely. We can interpret it as a sum of two curves, which I will draw here. You see, that's why I need the blackboard, where I got several cases. So I draw two curves here. One which would represent what I call N1, the number which will come if hole number 2 is closed by another piece of armor plate in front, and so they all come through number 1. And N2 would be the number that come through hole number 2 alone. So N1 is the number that comes through hole number 1 alone, and N2 is the number that comes through hole number 2 alone, those numbers being determined by closing the respective holes. And then we discover a very important law, which is that the number that arrive with both holes open is the number that arrive by coming through number 1 hole plus the number that comes through number 2 hole. And this proposition, the fact that all you have to do is add these two together, I call nice, or no interference. That is, what you get from the two holes open is the same as you get by simply adding each hole separately. That's for bullets. Done. We're done with bullets. All right, I begin again. This time with water waves. Here is standing some kind of a big mass of stuff which is being shaken up and down. This is a long line of barges or jetties with a gap in the water in between. Perhaps it's better to do it with ripples than it is to do it with big ocean waves that sound more sensible. I wiggle my finger up and down here, and I have a little piece of wood here, and ripples start out here, and then I've arranged in a tank to put boards in the way here so that I have these two holes. And then I have this so-called detector. Now, what I do with the detector, what the detector detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down. And what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves. Also, I forgot to say that this jiggling is made very regular and perfect so that the waves are all of the same spacing from one another, and then I'll describe what we get under those circumstances. For that, I first remark, well, let's see. First, we can measure the energy of the cork, but then another thing is important for light, for water waves, water waves, is that the thing that we're measuring can have any size at all. We're measuring the intensity of the waves or the energy in the cork, and if the waves are very quiet, if the fellow over here is only jiggling a little bit, then there'll be very little motion of the cork, and so on. No matter how much it is, it's proportional. So it can have any size. It doesn't come in lumps. It's not all there or nothing. And what we're going to measure is the intensity of the waves, which, to be precise if you want, is the energy generated by the waves at a point. And now what happens if we measure the intensity, which I'll draw on a third curve here, which I'll call I to remind you it's an intensity and not a number of particles of any kind, and I12, when both holes are open, is a curve that looks something like this. Another an interesting, complicated-looking curve, which ought to be symmetrical. I didn't do too badly, actually. A very complicated-looking curve. That is, if we put the thing in different places, we get a very, very different intensity, which varies very rapidly in a peculiar manner. And you're probably all familiar with the reason for that. The reason is that the ripples, as they come out of here, have crests and troughs spreading from here. And they have crests and troughs spreading from here. Now, if we're at a place which, say, is exactly in between these two things, so that the two waves arrive at the same time, the crests will come on top of each other, and there'll be plenty of jiggling, which is the exact opposite of this curve. So I'll have to put, there should be another bump. We have a lot of jiggling right in dead center. On the other hand, if I were to move to some point here, since I'm further from hole 2 than hole 1, it takes a little longer for the waves to come from 2 than from 1. And when 1 has a crest arriving, the crest hasn't quite reached there yet from 2. In fact, it's a trough from 2. So the water tries to move up and it tries to move down from the influences of the waves coming from the 2 holes, and the net result is it doesn't move at all, or practically not at all, and so we have these low bumps at that place. And then if you move still further over, you get enough delay that when a crest is here, this other crest is in fact one whole wave behind. So in fact it's a crest that is, 2 crests are coming on top of each other, but not the same crest, so to speak. The 4th crest from here and the 5th crest from there on top. So you get a big one again, then a small one, a big one, small one, depending upon the way the crests and troughs interfere, as we say. The word interference, again, is used in science in a funny way because we'll have what we call constructive interference. When they both interfere here, it makes it stronger. Well, they call it interference anyway, but the very important thing is that I12 is not the same as I1 plus I2, and we say it shows interference. Yes, interference. That's a funny term. We use it. Constructive and destructive interference. I didn't mention what I1 and I2 look like, but we can find out by closing this, for instance, to find I1. The intensity that you get here, if the hole is closed, is simply the waves from one hole for which there's no interference, and that's this curve. N1 is the same as I1, and the same way otherwise I2, and this curve is quite different than the sum of these two. As a matter of fact, the mathematics of this curve is rather an interesting one. What is true is this, that the height of the water when both holes are open is equal to the height that you would get from number 1 open plus the height that you get from number 2 open. Thus, if it's a trough, the height from 2 is negative and cancels out the height from 1. So you can represent it by talking about the height of the water. But it turns out that the intensity in any case, for instance, when both holes are open, is not the same as the height, but it's proportional to the square of the height. And it's because of this fact that we're dealing with the squares that we get these very interesting curves. All right. Now, We erase the machinery and start over. This time we start with electrons. We have a filament here, tungsten plate, holes in the tungsten plate, and for a detector, any electrical system which is sufficiently sensitive to pick up the charge of an electron arriving with whatever energy the source has. Or if you would prefer, we could use photons, and this is a black paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp hole, so use something better. And here, for a detector, a photomultiplier that can detect the individual photons arriving. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photon, is this. First, that what we receive in this electrical detector with a sufficiently powerful amplifier behind it are clicks. Click, 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 and so on, with the source here. Lumps. Absolutely lumps. When the click comes, it's a certain size, and the size is the same. If you turn the source weaker, the clicks come further apart, but it's the same size click. If you turn it up, they go click, 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 and it jams the amplifier. So you have to turn it down enough that there aren't too many clicks for the machinery that you're using to detect. Next, if you will to put up another detector here and listen to both of them, you never get 2 clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors. So that means that the thing which is coming comes in lumps. It has a definite size and it only comes to one place at a time. All right, so for electrons, or for photons, we'll just use electrons. It comes in lumps. And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneously. But let's suppose we put it in a certain place and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. It just one goes off, then the other goes off, then this goes off, then that one goes off, so on. Just like with bullets. And we measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive, the same kind of an N12 as before. This is what we get for N12. N12 is this what we get with both holes open. And that's the phenomenon of nature, that she produces the curve, which is the same as you would get from an interference of waves. But she produces a curve for what? Not for the energy in a wave, but for the probability of arrival of one of these lumps. The mathematics is simple. You change I to N, and you have to change H to something else, which is new. You call it something because it's not the height of anything, but in order, this curve has a simple mathematical form. There's an A, which can be represented as an A1 plus an A2, which we call a probability amplitude, because we don't know what it means, which to arrive from hole 1 plus the probability amplitude to arrive from hole 2, and you add the two together to get the total probability amplitude to arrive and square it. Just direct imitation of what happens with the waves, because we've got to get the same curve out, so we use the same mathematics. Let's find out, I better check on one point, though, about the interference, I forgot to say. What happens if we close one of the holes? Let's try to analyze this interesting curve, which now, for electrons, I erase all the stuff with the light. Well, everything with light is erased. And now we're talking about electrons. This curve isn't important in our case. This is the number which arrives. Now, we would like to analyze this curve. And we try this. We say maybe it comes, we can analyze this by thinking that the electrons come through this hole or through the other. So we can close one hole and measure how many come through hole number 1, and we get that curve. Or we can close this hole and measure how many come through hole number 2, and we get that curve. And these two added together is not this, and so this is not the same as N1 plus N2,
And it does show interference. It shows interference. And in fact, the mathematics is given by this funny formula that the probability of arrival is the square of an amplitude, which itself is the sum of two pieces. Now, the question is, how can that come about? That when they go through hole 1, they would be distributed this way. When they go through hole 2, they would be distributed that way. How could it be that when both holes are open, you don't get the sum of the two? Instance. If I hold the detector at this point here, I get practically nothing. If I close one of the holes, I get plenty. If I close the other hole, I get something. If I leave both holes open, I get nothing. If I let them go through both holes, they don't come anymore. Or take the point in the center. You can show that that's higher than the sum, than it was in the other case, than the sum of these two. I get more here when both holes are open than I would get with either one of the two closed. Now, you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated, or it splits in half and goes through the two holes, and so forth, in order to explain this phenomenon. Nobody, however, has succeeded to get an explanation of this that's satisfactory, because the mathematics in the end is so very simple. The curve is so very simple. I will summarize then by saying that electrons arrive in lumps, like particles. But the probability of arrival of these lumps is determined like the intensity of waves would be. And it is in this sense that the electron behaves, as you might say, sometimes like a particle and sometimes like a wave. It behaves in these two different ways at the same time. And that's all there is to say. I give a mathematical description to figure out the probability of arrival of electrons under any circumstances and so on, and that would, in principle, be the end of the lecture, except that there are a number of subtleties involved in the fact that nature works this way. There's a number of peculiar things. And I would like to discuss those peculiarities because they may not be self-evident at this point. So to discuss the subtleties, we begin by discussing a proposition which we would have thought to use since these things are lumps. Since what comes is always one complete, which I'll call an electron, one complete lump, one complete electron, it's obvious that it's reasonable that either an electron arrives or goes, let's say, that either an electron goes through hole number 1 or it goes through hole number 2. That seems like it goes through hole number 2. That seems very obvious that it can't do anything else if it's a lump. And I'm going to discuss this proposition, so I have to give it a name. I'll call it Proposition A. Now, we've already discussed a little bit what happens with Proposition A. If it were true that an electron either goes through hole number 1 or it goes through hole number 2, then the total number which arrive here would have to be analyzable as a sum of two contributions. The total number which arrive here will be the number that come here via hole 1 plus the number that come via hole 2. And since this curve cannot easily be analyzed as a sum of two pieces in such a nice manner, and since the experiments which determine how many would have arrived would have arrived, if only hole number 1 were open, don't give the result that this number is the sum of these two, it is obvious that we should conclude that this proposition is false. It is not true that the electron either comes through hole number 1 or hole number 2. Maybe it divides itself in half temporarily and so on. So proposition A is false. That's logic. Unfortunately, or otherwise, we can test logic by experiment. And so we just have to to find out whether it's true or not that the electrons come through hole 1 and hole 2, or maybe they go around through both holes or they split up and so on. All we have to do is watch them. When we watch them, we need light. So we put back here behind the holes a source of light. It's very intense light. Light is scattered by electrons. It is bounced off electrons. And in other words, you can see electrons if they go by if the light's strong enough. So we stand back here and we look to see whether we see, when the electron is counted here, a flash, or have seen the moment before the electron's counted here, a flash behind hole 1 or a flash behind hole 2, or maybe a sort of a half flash in each place at the same time. Because we're going to find out now how it goes by looking. Well, you turn on the light and look, and lo, you discover that you see flashes behind either one hole or the other hole every time you get a count here. Every time there's a count here, you see a flash behind number 1 or behind number 2. What you see is that the electron comes 100% complete through hole 1 or through hole 2. When you look, kind of a paradox. Well, let's squeeze nature into some kind of a difficulty here. I show you what we're going to do, see? We're going to keep the light on, we're going to watch. And we're going to count how many electrons come through. And we're going to make 2 columns. I'll watch the holes very carefully while you please count how many are arriving in the detector. All right, you say, 1 arrived. I said, I saw that when it went through hole number 1. So we put here 2 columns, which is column 1 for number 1 hole and number 2 hole. And every time you get one, you tell me you got one. I have seen it, of course. And I say either number 1 or 2. The first one was 1. What's the next one? Number 2. All right. Number 2. Number 2. Number 1. So on. So as we watch the electrons, as I watch the electrons, for every one that you count, I can separate them experimentally into 2 columns. Them are what have arrived via hole 1, and those, I know the English is right, I'm just trying to, that arrived via hole 2. So the number, the total number that arrived, well, first, what does this column look like when you add it all together for different positions here, which is just the number that is supposed to have come through 1. I watch behind 1, and what do I see? I see this curve. That number column is distributed this way. Just like we thought when we closed hole 2. It works the same way whether we're looking or not. If we close hole 2, we get the same distribution in those that arrive as if we are watching. And likewise, the number that in this column that is supposed to have arrived via hole number 2 is also this simple curve. Now look, the total number which arrived has to be the total number. I'm just counting little marks. It has to be the sum of this number plus that number. The total number which arrived absolutely has to be the sum of these 2. It has to be distributed this way. But I said it was distributed this way. It's distributed this way. It really is, of course, it has to be. It is. It's distributed this way. If then we mark with a prime the results when a light is lit, prime means with a light lit, then we find N1 prime is practically the same as N1 without the light, and N2 prime is almost the same as N2. But the number that we see when the light is on is equal to the number that we see through 1 plus the number that we see through 2. This is the result that we get when the light is on. In other words, we get a different answer whether I turned on the light or not. If I have the light turned on, this is the distribution which you measure over here. If I turn off the light, this is the distribution that you measure over here. Turn on the light, this is the answer. Turn off the light, that's the answer. See, nature squeezed out. Now, we could say then that the light affects the result. If the light is on, you get a different answer than if the light is off. If you want to, you can say the light affects, it does affect. In fact, we found this by this experiment. We get a difference with the light on and off. Light affects the behavior of electrons. If you want to talk about the motion of the electrons through here, which is a little inaccurate, you can say that the light affects the motion, so that those which might have arrived at the maximum are somehow been deviated or kicked by the light and arrive at the minimum instead, so smoothing the curve to produce this thing. You see, electrons are very delicate. Although when you're looking at a baseball and you shine light on it, doesn't make any difference. The baseball goes the same way. Electrons are very flimsy, very delicate. And when you shine the light on them, it's a little tough on the electron. It knocks them about a bit. And instead of doing that, they do this, because you turn the light on so strong. You hit them with a hammer. It's not just a delicate thing like when you're looking at a baseball with light. They hit them with a hammer. But you turn up the light too strong. Turn it weaker and weaker and weaker until it's very dim. And then use very careful detector that can see very dim light. And look with the dim light. Now, as the light gets dimmer and dimmer, you can't expect with very, very, very weak light to affect the electron so completely as to change the pattern 100% from this pattern to this pattern. As the light gets weaker and weaker and weaker, somehow it should get more and more like no light at all. And how then does this turn into that? Well, it turns out that light is not like a wave of water, but light also comes in particle-like character called photons. And as you turn down the intensity of the light, you're not turning down this effect, you're turning down the number of photon particle-like things that are coming out of the source. So as I turn down the light, I'm getting fewer and fewer photons. The least I can scatter from an electron is 1 photon, and if I have too few photons, well, sometimes the electron will get through, and it just happened there wasn't enough light. There was no photon coming by. I didn't see it. So a very weak light doesn't mean a small disturbance. It just means a few photons. And what happens is that I have to invent a third column. You see, you get a click over here. I say, I saw that one. That was in number 1 hole. This one behind hole number 2. Then another sorry, I didn't see that. There wasn't enough light to give a photon at that time, so there must be a third column under didn't see. And when the light is very strong, there are very few in there. When the light is very weak, most of them end in there. So that there are 3 columns, this one, and sometimes in here. Now you can guess what happens. The ones I do see are distributed this way. The ones I didn't see are distributed that way. And as I turn the light weaker and weaker, well, I see less and less of them. A greater and greater fraction are not seen. And the actual curve, in any case, is a sum of a mixture of this, and as the light gets weaker, so that fewer and fewer are seen, it gets more and more like that in a continuous fashion. So, in this case, if the electrons are not seen and nothing bounced off the light under those circumstances, you get this complicated pattern for those electrons which were not seen. The ones in the column didn't see are exactly distributed in this complicated way, and the other 2 columns are in these 2 ways here. Now, you say, I got another way to measure which hole it goes through. And I'm sorry I haven't got enough time to discuss a large number of different inventions that you might have to find out which hole the electron went through and what happens in each case. It always turns out, however, that it's impossible to arrange the light in any way so that you can tell through which hole the thing is going without disturbing the pattern of arrival of the electrons from this form to this form, without destroying the interference. And not only light, but anything else. You use neutrinos, you use anything. There's a principle that's impossible to do it. You can, if you want, invent a way to tell which hole the electron's going through. Then it turns out it's going through one or the other. But if you try to make that instrument so that at the same time it doesn't disturb the motion of the electrons, then what happens is you get back, you can't tell anymore which one it goes through, and you get this. If you can tell, you get this. Heisenberg noticed when he discovered the laws of quantum mechanics that the new laws of nature that he discovered could only be consistent if there was some basic limitation to our experimental abilities that had not been previously recognized. In other words, you can't experimentally be as delicate as you wish. And he proposed his uncertainty principle, which stated in terms of our experiment is the following. He stated it another way, but they're exactly equivalent. You can get from one to the other, but unfortunately I haven't time to explain that. But in our experiment, his uncertainty principle would be stated in this manner. It is impossible to design any apparatus whatsoever to determine which hole the electron passes. And when one succeeds in determining which hole the electron passes, which can determine through which hole the electron passes. That will not at the same time disturb the electron enough to destroy the interference pattern. And no one has found a way around this. And I'm sure you're all itching with inventions as to methods of detecting which hole the electron went through. But if each one of them is analyzed carefully, you'll find out there's something the matter with it, and that if, without disturbing the electron, you think you could do it. But it turns out there's always something the matter, and you can account for the difference in the patterns due to the disturbance of the instruments used to determine through which hole the electron comes. Now, this, therefore, is a basic characteristic of nature and tells us something about everything. If a new particle is found tomorrow, the kaon, actually it's already been found, something, give it a name, let's say a kaon, and I used kaons to interact with electrons to determine which hole the electron is going through, I already know ahead of time, I hope, enough about the behavior of the kaon to say that it cannot be of such a type that I could tell through which hole the electron would go without at the same time producing a disturbance on the electron that changed the pattern from here to here. So that uncertainty principle is used as a general principle to guess ahead at many of the characteristics of unknown objects. They are limited in their character. Well then, let's go back. What about this proposition A? Does it go either through one hole or the other, or not? Well, physicists have a convention, a way of avoiding the pitfalls which exist, and they make their game, their rules of thinking as follows. That if you have an apparatus which is capable of telling which hole the electron goes through, and you can have such apparati, then one can say that it either goes through one hole or the other. And it does when you look. It always is going through one hole or the other when you look. But when you do not try to determine, or you have no disturbance, no apparatus there to determine through which hole the thing goes, under those circumstances, you cannot say that it either goes through one hole or the other. You can always say it, provided you stop thinking immediately and don't make any deduction from it. We prefer not to say it, rather than to stop thinking at the moment. In other words, when we don't look, we can't say through which hole it's going, but if you try to look to see, you find it always goes through one hole or the other. Still, to conclude that it goes either through one hole or the other when you're not looking is to produce an error in prediction. And that is the logical tightrope on which we have to walk if we wish to interpret nature. This proposition that I'm talking about is more general. It's not just for two holes. It's a general proposition reads something like this, that the probability of any event in an ideal experiment, that just means that when everything is specified as well as it can be, the probability of an event is the square of something, which I call A here, is called the probability amplitude. And when an event can occur in several alternative ways, the probability amplitude, this A number, is the sum of the A's for each of the various alternatives. And finally, if an experiment is performed which is capable of determining which alternative is taken, the probability of the event is the sum of the probabilities for each alternative. That is, you lose the interference. Now, the question is, how does it really work? What machinery is actually producing this thing? Well, nobody knows any machinery. Nobody can give you a deeper explanation of this phenomenon than I have given. That is a description of it. They can give you a wider explanation in the sense that they can do more examples to show how it's impossible to tell which hole it goes through and at the same time not destroy the interference pattern. They can give a wider class of experiments than just the two-slit interference experiment and so on, but they're just repeating the same thing to drive it in. It's not any deeper, it's only wider. The mathematics can be made more precise. You could mention that they're complex numbers instead of real numbers and a couple of other minor points which have nothing to do with the main idea. And the deep mystery is what I described. And no one can go any deeper today, but only wider. Now, I mentioned probabilities in this calculation. What we're calculating here, this curve, is the probability of arrival of an electron. The question is there any way to determine where it really arrives? We are not averse to using the theory of probability, that is calculating odds, when a situation is very complicated. You throw up a die and it spins so many times in the air with the various resistors and atoms and all this complicated business that we're perfectly willing to allow that we don't know enough details, and so we calculate the odds that the thing will come this way or that way. But here what we're proposing, is it not, is that there be probability all the way back at the fundamental laws. That in the fundamental laws of physics there are odds. For example, suppose that I have an experiment so set up that with the light out, I get this interference situation and know that. Then I say that with the light on, I can't predict through which hole it will go. I only know that each time I look, it'll be one hole or the other. But there is no way to predict ahead of time through which hole it goes. The future, in other words, is unpredictable. It is impossible to predict in any way from any information ahead of time through which the thing will go, or which hole it will be seen behind. That means that physics is kind of given up if the original purpose was, and everybody thought it was, to know enough that in given the situation, you can predict what's going to happen next. Given the circumstances, you can predict what happened. Here are the circumstances. Source, strong light source, tell me which hole, behind which hole will I see the electron? You say, well, the reason you can't tell through which hole you're going to see the electron is it's determined by some very complicated things back here. If I knew enough about that electron, it has internal wheels, internal gears, and so forth, that the fact, and that this is what determines through which hole it goes. So it's 50-50 probability because like a die, it's set sort of at random. And that if I were to have studied it carefully enough, your physics is incomplete. If you get a complete enough physics, then you'll be able to predict through which hole it goes. That's the hidden variable theory, so-called. Well, that's not possible. It is not due to a lack of detailed knowledge that we cannot make the prediction, because I said that if I didn't turn on the light, I should get this interference pattern. If I have a circumstance in which I get that interference pattern, then it is impossible to analyze it in terms of saying it goes through here or here, because that curve is so simple, mathematically a different thing than the contribution of this and this as probability. So if it were possible for you to have determined through which hole it was going to go if I had the light on, the fact that I have the light on hasn't got anything to do with it. Whatever gears there are back here that you observed, which permitted you to tell me whether it was going to go through one or two, you could have observed if I had the light off. And therefore you could have told me with the light off which hole, each time an electron goes, which hole it's going to go through. But if you can do this, then that curve would have to be represented as the sum of those that go through there and those that go through there, and it ain't. And therefore, it's impossible to have any information ahead of time as to which hole it's going to go through when the light is out, or when the light is on, or out, in a circumstance where the experiment is set up there can produce this interference. So it is not a lack of unknown gears, a lack of internal complications that makes nature have probability in it. It seems to be in some sense intrinsic. Someone has said it this way: nature herself doesn't know which way the electron is going to go. A philosopher once said, pompously, "It is necessary for the very existence of science that the same conditions always produce the same result." Well, they don't. You can set up the electrons in any way. I mean, you set up the circumstance here in the same conditions every time, and you cannot predict behind which hole you'll see the electron. They don't, and yet the science goes on in spite of him, although the same conditions don't produce the same results. That makes us unhappy that we can't predict exactly what will happen. Incidentally, you can make a circumstance which is very dangerous and serious, and man must know, and still can't predict. For instance, we could cook up, I know we'd rather not, but we could cook up a scheme by which we arrange photocells so that if it sees the electron, one electron is going to go through. If we see it behind hole number 1, we set off the atomic bomb and start World War III. If we go see it behind hole 2, we have just make peace feelers and delay the war a little longer. Then the thing is that the future of man would then be dependent upon something which no amount of science can predict. So the future is unpredictable. What is necessary for the very existence of science and so forth, and what the characteristics of nature are not to be determined by pompous preconditions. They are determined always by the material with which we work, by nature herself. We look and we see what we find, and we cannot say ahead of time successfully what it's going to look like. The most reasonable possibilities turn out often not to be the situation. What is necessary for the very existence of science is just the ability to experiment, the honesty in reporting results. The results must be reported without somebody saying what they'd like the results to have had been, rather than. And finally, an important thing is the intelligence to interpret the results, but important point about this intelligence is that it should not be sure ahead of time about what must be. Now, it can be prejudiced and say that's very unlikely. I don't like that. Prejudice is different than absolute certainty. I don't mean absolute prejudice, just bias. But not strict bias, see, not complete prejudice. As long as you're biased, it doesn't make any difference, because if the fact is true There will be a perpetual accumulation of experiments that perpetually annoy you until they cannot be disregarded any longer. Only can be disregarded if you're absolutely sure ahead of time of some precondition that science has to have. In fact, it is necessary for the very existence of science that minds exist which do not allow that nature must satisfy some preconceived conditions like those of our philosophy.
Yes, Santoshi, you want to say something?